Good morning, everyone. So similar to how Mark started the day yesterday, for the astute observers in the room, I am not Ben Worrell, no matter what the schedule says. But I really, it feels weird having an NRRA conference without Ben Worrell. So I took the most recent picture I had of Ben and I AI generated him in a sling so he could be here with us today. Ben, we know you're listening in online. Please feel free to correct anything I say in the chat. And then thanks for the help putting these slides together today and letting me have the fun. But just a warning, the contents of my slideshow have been modified from Ben's original version. So now you get Michael's version of the presentation this morning. So I am really excited to be the one that gets to kick off and introduce NRRA Phase 3. And then I'll also be talking about some upcoming MnROAD construction opportunities and then the tour that we're doing this afternoon. So NRRA solicitation. So I think a lot of this, most people in this room have already seen, but we have the different commitment levels based on your state's SDNR funding. And then we've also been able to add different additional funding options for individual NRRA agencies really to make this work for them. And this pooled fund. So the pooled fund is officially approved. The acceptance letters are completed. There is money in the accounts. Agencies are committed. So we are officially up and running almost 2 months in now. So we are 2 months into our 5-year NRRA pooled fund. We have nice coverage, especially in the upper Midwest, but also all the way down to Georgia with some of our beta projects and beta groups, including New York, California. We are always interested in getting new members, but we really like the kind of function that we have going with the NRRA right now, where we have a good group of active participating agencies and states, and we are able to accomplish a lot within our group and our room. But if there are other agencies, bring them along. We're always looking to grow and looking for more expertise and more ideas to help the research move along. So kind of overall structure, as everybody knows, and kind of the agendas followed today, the NRRA, National Road Research Alliance, is divided into 5 kind of functional teams, being the flexible team, the rigid team, preventative maintenance, geotech, intelligent construction, and then the executive committee that kind of oversees the whole show. Ben wanted to encourage the discussion as far as team chairs. Really, the takeaway is we're not necessarily looking for new chairs, but if there's new volunteers, we're always open to new ideas. We don't want to put people like Kurt Dunn or people that have been there for a longer time. We don't want them to be waiting to wait out their term when there is no kind of term limit or anything like that. So not pushing anybody out, but always kind of looking for relieving the pressure on kind of the Kurtz and the Tylers, the Rovels. It is a little bit of a burden. We try within MnDOT, especially our research group, to provide support, but really want to acknowledge and thank the team leads of each of these teams. And then there's also the floating green box here, which is kind of the unnamed green box. It was the low carbon working group, renamed to life cycle group. This is still something we're considering doing. I spoke with Emil earlier this week. As of now, we're going to hold off from making it an official team. But really, if there is interest or discussion in this area, talk to Emil. He's kind of informally got a group together, and we'll see what that grows into. There's a lot of, I think, national interest in continuing the sustainability conversation and looking for a venue, a neutral venue like NRRA, where we can bring in agencies, industry, different industries, concrete, asphalt, aggregate producers, all of that into this kind of sustainability working group, low carbon working group, whatever we end up deciding to call it. Talk to Emil if you're interested in those initiatives. throughout, I added my little pop-up face when I'm going to add my 2 cents and kind of step away from Ben's plan stuff. To me, it's the people that have really made NRRA successful and function. So I was hired at MnDOT 9 years ago as a temporary employee for two-year temporary employee in 2017 because we had an influx of MnROAD construction resulting from this pooled fund. What Jeff Brunner had told me at the time was, we don't know how this pooled fund is going to carry on. We can't promise any long-term employment. But that's kind of what I came into. So I was year 1 or 2, kind of the first MnROAD construction. I remember sitting in the conference room at Maplewood. We would sit in our circle for a team meeting. We would dial in on the conference phone. We had a dial-in number. But it was fun to sit in the room. It was Dave Van Dusen at the time, and then it was Dan Ash from Missouri. But really, it's the people and the flexibility of the NRRA that makes this successful. Everybody in this room. So a lot of what I'm talking about on phase 3 is unknown, undetermined. It's exciting. I know it's going to be good, but it is what we make it as a group. So executive team members, like to acknowledge them in their time as well. And then some really important MnDOT people that we do not give enough credit for. And as we're into phase 3 of the study, really need to acknowledge kind of the behind the scenes MnDOT people that make this work. So Jackie, Duran, and Hafiz here. Do you mind standing, Jackie? I warned you yesterday, Hafiz, so please stand. Thank you both for all that you do. So for the PIs in the room, Hafiz and Jackie are the point of contact from MnDOT Research Services, handling a lot of the contract management, keeping the tasks, the projects moving. I wanted, if you're a PI and you haven't met them before, make a point to go and meet them and shake their hand. Sometimes you get scary automatic emails from Hafiz that say a task is overdue. He's a lot nicer than those automatic emails sound. So don't be afraid of Hafiz. Don't be afraid of Jackie. They're great to work with, and they really do a lot behind the scenes that make NRRA function. And then our consultant services and contracting. As you all know, we do have a lot of research contracts that MnDOT initiates, so it is a larger burden on that staff as well. So thank you everyone here for being patient with that and the large contracts that we've all pushed through, and then MnDOT Consultant Services for handling all of that. And then our district and materials engineers. One, thank you for coming, and also we pick on you a lot for research, and thanks for being receptive to us and supportive for us. Things that we can't do at MnROAD, we're able to kind of work into our districts, and we really value and appreciate that relationship. All right, so outreach activities. So we have the research pays off seminars, team meetings, and this is all kind of evolved throughout the different phases. And that's one of the things that I like the best, and I think is help NRRA stay relevant throughout the 3 different phases, is we're always willing to switch things up. We're not too set into any rigid rules or formats, or if the team needs a meeting or doesn't need a meeting. And it's really that kind of flexibility that I think has allowed us to find our niche with all the other organizations out there. So if you have any ideas for continued improvement, please always feel free to share your feedback and continue provide feedback to your own team, but take time to sit in on another team and learn from kind of what the other groups are doing as well. All right, so now that we do have phase 3 money, we have a backlog of phase 2 projects that we needed to kick off. So the perpetual pavement test section. So we have a test section in MnROAD, and then a test section in Osseo, Wisconsin. And then the spray rejuvenator study, the year 3 of that, over predicted resistance of non-displacement piles and sands, beta enhancements, and then low carbon monitoring extension. So all of those are either in the process of consultant services, releasing contracts, or internal MnDOT finalizing the RFP. So those will be finalized and posted within the next couple months. And that leads us to probably the most exciting slide that I have today, but the call for research for 2027-28 construction. So we'll have a formal call coming soon, June 31st-ish. I'm going to put the caveat there. We've had a lot of, within the last week, a lot of internal discussion on setting the dates and kind of, okay, if we want to be constructing interstate test sections or a large letting for test sections in May or June of 2027, we better start deciding right now what those test sections are going to be and really get in the planning and the letting and those processes going. The sooner the better, as far as we get our data, we get our plan sets, we can get everything moving, really working towards construction next summer. So this call for research, there's a lot that still needs to be defined as far as the formal call. So we're going to be having an executive committee meeting in the near future, kind of defining the parameters of this. But this could be research only projects. Doesn't need to be MnROAD related. Really, it's the team's decision on whether they want to use that money for MnROAD related research or something else that fits their team's agenda. So it's really all going to be member driven as far as what projects get selected and research and construction ideas. So start throwing out your ideas, start planning, start brainstorming. As you're on the tour, start thinking of what type of research would really help you and your agency and your position moving forward as we start building this phase 3. All right, so now moving to construction. Ben and I got our hard hats on. So real quick, just wrapping up some of the small construction stuff we did last year. We constructed the phase 1 of the flooded road test section. This is actually a tour stop on the tour this afternoon, so we'll talk a lot more on site. Jacob Cowher will be there talking about the construction here. But this was the old farm loop study that was done in the MnROAD stockpile area, kind of in the 2008 time range. So we had the existing pavement. We added the berms on the side, some plastic, and the whole idea is we tested the pre-existing kind of condition last summer or last fall with the FWD, the thaw through this winter. And then this year, we're going to install some moisture sensors and then actually have our first flooding event and then monitor strength as the pavement dries. This is not a funded research project yet. It was one of those last year where it was something we had talked about for a couple of years. We had the real estate and we should start building this and determining functionality, and then we have more real estate here that you'll see today for multiple phases or other iterations, but this was kind of our first step starting off with this research initiative. So the other project that I was going to talk about, I have 10 slides for. It was exciting MnROAD asphalt construction that was not NRRA, but it happened last summer. We didn't have anything planned. But we had companies step up and actually pay for the construction costs at MnROAD. We had the real estate available, we have the monitoring tools, and we had 3 companies that really wanted to get their products in the field, start getting field testing, winter performance especially is kind of the unique niche that we have at MnROAD and the low temperature cracking. So these companies stepped up and paid for their construction costs. I'm going to skip through experimental setup. Want to highlight the companies real quick and acknowledge them. So we have High-Tech Solutions with a cellulose fiber, Renew Core by Certainty, which is a pelletized shingle, and I'll talk about it more in the tour discussion. But Mari Krieger is here and will be doing a presentation at MnROAD this afternoon. And then as well, after that, you can take people out to the test section if you're interested. We had Genable Pavement by Universal Matter. That's a graphene additive aimed at being an SBS replacement. And then a AdForce St. Gobain interlayer. So between asphalt interlayer, looking at mitigating reflective cracking. I'll show some of the construction photos real quick. So this was all done with Caterpillar paving team, milling and paving. So the partnership that we have with Caterpillar, the product participants purchased the mix from the hot mix plant and paid for the trucking, brought it to MnROAD. Caterpillar did all of the paving and paving compaction, everything else, milling on their own, so with their team. So that was a nice tie with this, and we were able to cut some costs with that. So here's the glass field grid layer. And then acknowledgements. All right, so now looking forward to future construction. So we have MnROAD flooded road. We'll be doing sensor installation on that. We have a pavement buckling experiment that Tom Burnham and the Rigid team are putting together. And then a bender element experiment, which is a sensor study through the University of St. Thomas. It's a Minnesota Local Road Research Board and not an NRRA study, but it is one of our construction activities for the summer. All right, and then looking forward to the following construction seasons, 27 and 28. We're planning on 2 unique construction lettings, both the main line and the LDR. Again, it'll be member driven. And then lastly, it's that last line that we have. It's most important. We have money. That's what that last line means. So both MnDOT construction money and NRRA research money, we're in a really nice position right now where we have flexibility, we have money, and we get to have fun over the next couple months to figure out what we can do experiment-wise that is the most value for that money. All right, so looking into kind of my crystal ball of what we see, none of this is binding, just as we've had some internal conversations. So 2027 construction is likely to be more rigid team, more concrete pavements than flexible pavements. The rigid team has a backlog, especially on the low volume road. It's with our CAT partnership that I mentioned, it's a lot easier for us to do smaller asphalt, low volume road experiments. There's a lot more asphalt pavers in the state of Minnesota than there is concrete pavers. So it's a lot easier for us to mobilize and do smaller projects on a low volume road for asphalt than we are for concrete. So there's a bigger backlog of the concrete test sections and experiments. And then 2028 also kind of fits the cycle with the MnROAD and NCAT partnership. So we'll be doing some of the new asphalt test sections will be a part of the MnROAD NCAT Next Pave Challenge. And the way that challenge is set up, or the way that study is working, in 2027, they're going to build test sections at the NCAT test track. And then the following year, we'll build companion sections here in 28, getting that north-south regional comparison. I really want to encourage everybody to start brainstorming. So we have some ideas to reclaim existing cells. We like to keep the balance that we have between concrete and asphalt and reclamation and preservation and kind of geotech specific test sections. We're not trying to dominate one way or the other. Really want to start collaborating between the teams. Building off some of the conversations that we had yesterday, just going off the flex team stuff. And like Joe Bowles mentioned and kind of the discussion with Ishan, some of our network-based conditions, subgrade conditions are really driving our pavement distress. And I think it'd be cool to collaborate together and see if I can out asphalt a bad subgrade, or if you can out subgrade bad asphalt or something in between, but playing with those kind of variables and looking at the whole structure and not just specific elements that we have. All right, so apparently when I asked to turn us into tour guides, it's a safari tour, and I got the sling this time. So thanks, Ben. So tour guide, now switching to the tour quickly. So tour is this afternoon. At MnROAD, we have maps and directions on the table outside, just safety stuff right up front. We do not have a track or our truck on the low volume road. There are still trip hazards. Our ditches get a lot of trenches. They're uneven. So especially if you're walking in the shoulder, look out for trip hazards. The pavement, we have good condition right now, so there's less trip hazards there. But there are uneven surfaces. Other big thing to notice that I didn't put on here, if you are walking in the ditches or the grass, we've started to seeing ticks in the last couple of weeks. So please be aware of that, and double check as you get in your vehicles and leave. We'll travel kind of on the inside lane, or we'll have cones guiding traffic, and then vests are required, so if you have one, bring it, otherwise we have lots of them at MnROAD. So MnROAD tours to me, I kind of view as my 3-year-old son having a play date, and he takes out every single toy we own in the first 30 minutes. And then they decide what they like, and then they play with one of them after everything is out for the next hour. So really want to leave that decision to you all on what is exciting and what you play with in the 2 hours you have at MnROAD. So it's choose your own adventure. We have 2 tours. It's the exact same tour. It's going to repeat twice. At the same time as we have the first tour, we'll have the vendor demonstrations and presentations going on in the conference room. So if you choose to go to the vendor presentations, then you can do the tour after, or you can skip the tour and go with the vendors after, or whatever you'd like to do. General schedule: tour will leave from the front of the building. We'll be taking our own vehicles. We've got some MnDOT vehicles that you can jump in, and we can carpool a little bit, but in general, we'll be using our own vehicles. We're not going to make everybody walk the whole thing. And we'll do this multiple times. And if you get stuck at stop 1, talking to Jacob on the flooded road in the first tour, and you stay there for the next hour and a half, good for you. That's exactly what we want. So stay where you're interested. Don't feel like you're obligated to keep up with the group. I'll have the air horn. I'll keep the group moving, just for those that want kind of the full tour, but really want to have you all have the freedom to go where you're interested in. Mentioned Renew Core and Seismic in the main rooms. And then we'll also have Thomas Calhoun with MnDOT's Road Doctor. We'll have snacks. We'll have cooler with water. So this is really why we're driving. Our first stop is the flooded road test section. It's in our stockpile area. So to get there, we are traveling out of MnROAD facility, so back on a public roadway. It's a mile away. We'll travel there as a group, but it is a public roadway, so we yield to public traffic. And then Jacob will talk in the stockpile area. Then we'll come back into MnROAD. Tom Burnham will talk some concrete. And then we'll move further down, and we'll go to Sharon and Raul, who will be installing the corner reflector sensors with the team from Auburn that we saw a presentation on yesterday. So they'll also be talking some geotech sensor stuff as well, but you'll get to see that corner reflector being installed. And then we'll make our way around the loop, and then we'll talk asphalt and asphalt instrumentation, and then back to the building. Last slide, I added a sling to this guy, so we miss you, Ben. We're thinking of you, and thanks.
My name is Joseph Podolsky. I'm the MnROAD Research Implementation Engineer, and I'm going to be presenting about data availability for the MnROAD database. And, first off, I would like to thank Tom, who's here, and Mark, and Ben, who's online, for I guess support and guidance through this whole process of rewriting everything dealing with the database. And then I would also like to thank the other road research staff for a lot of their history dealing with the data. So, why does data availability matter? Data availability matters because a lot of decisions at MnDOT, they rely on the pavement roadway data. It helps for selecting and prioritizing projects and concerns towards chip and stip. It helps allocate the funding strategically, and then it also helps choose the right treatments. And then you design the pavement materials, gives you those ground specifications, like making changes within the specifications, and then monitoring and forecasting performance. So like here on the right, you have the seasonal load limits. A lot of the data that was used to build that whole entire process was from MnROAD. And we still supply some of the data that's part of the seasonal load limits And then right now, we're doing testing at MnROAD, looking at new equipment in terms of seasonal load limits. I think it's the vendor and development. So I don't know more about it. That would be more internal. You'd have to talk to Tim Anderson, but I don't think he's here. So
I'm here. Oh, you are here.
okay, you can talk to him. He's right there. I didn't see him. So, okay, but we have decades of world-class data at MnROAD. How do we make sure people can find and use it? That's the biggest question. What's inside the database? We have materials and lab results. There's instrumented sensors, there's static and dynamic data. We got traffic and loading. Right now, the traffic and loading is just the I-94 main line and the low volume roadway. We also have past data from Old Westbound as well. But it's no longer going to be part of MnROAD. So, and then we have 2 on-site weather stations as well. And then we do, I guess the bread and butter is the performance monitoring. So we get distress ride, running, all of that stuff. And then all this is integrated via InfoPay through the LTPP. And then you can like search and look for, download the data. You can also request data from the MnROAD staff as well. So when you make data requests, there is a request page online, but you can always contact Ben, Mike Wallace, or myself if you need something more specific. Because sometimes when you go through that page, it's just, you might say, I want everything, but then you're just gonna hear back from us that you really want everything because you don't know what's in there. So it's good to talk to us first sometimes before you request it. And these are just examples of what some of the data we have within our database. So that's a year's worth of data from cell 3 in 2013 from the thermocouple sensors. And then that's vehicle wander data that's from our weigh in motion system. And that's about 2 months of data. So that's like 60 some odd thousand vehicles. And it just shows like basically how much do the vehicles like stay for loading. And that's only commercial vehicles. So that's like class 4 and above. So this is how the data is structured and stored. So this very simplistic diagram shows the structure of how the data goes in the database. So so first we have a lot of the core tables, field monitoring, traffic data, and dynamic sensor output. We have researchers that basically have to put all that data manually into spreadsheets. And then we have to turn that over to our database manager. And then, so that can go into the database. So that's all manual. Then we have field monitoring, FWD testing, and we use a Microsoft Access loader to do edits, and then that helps push it straight into the database. We have a online system or interface that helps us put in field observations like the semi-lamp count, repairs, like a section timeline history, as well as traffic surface. In that interface now, we're also have the ability to add in like new sections, the layers, as well as sensor information. And then we have the environmental sensors that get loaded in twice a day, which is like pavement temp, air temps, moisture, vibrating wire data, all that sort of stuff. And so all of that data ends up going into the MnROAD database. So the MnROAD database is housed in Oracle, and that picture on the right is a really old picture of the database, like architecture overview. And we use Oracle SQL Developer to run queries to pull the data out. And so that was part of the reason about when you guys ask for all the data, we have to ask the question, do you really want all of it? Because it's not easy pulling everything out, because you have to run multiple queries just to get every set of data out for that section. And you might not want everything, and it might take a long time. So in the future, what we're trying to do is we're trying to standardize a lot of the data environment right now to make it more consistent, so that there's tables that aren't left connected to each other. And then we're trying to update our loader as well right now, so that we can, I guess, automate things to load quicker into the database, as we're doing construction. So here's another page on how do users access data today. So as I said before, you can do request forms, they're right there. We also have internal data share where people within road research or in our building or the districts that might ask for data, then we have to go and run a query, find the data, and then we have to export it. The problem is all the exports go into CSV files, so then you're limited. You can't have more than 1 million rows data, and some of the data sets are much longer than 1 million rows. So there's also public facing downloads, which are from InfoPave, and then we have a lot of documentation on our website, like there's contact information. There's also documentation about the sensors. And then we also have data dictionaries as well. So we have some gaps, challenges, and also user pain points. So what's hard today is, I guess, discoverability. Sometimes there's old tables in our database that we don't exactly know about because not all of us have been at MnROAD since the beginning. Tom has been here. He knows most of them, but even he might not know some of them either, because sometimes they get put in by others who have left and retired or they've gone to a new job. And so it's hard to figure out sometimes, why is this table here? What do we do with this data? Can we get rid of it, or do we still need to keep it? There's also metadata depth and consistency across the vintages, just making sure everything stays consistent. So that way we know something is related to something else. There's also large files, which we got to do a little bit better job of, I guess, doing filtering and then quick views. And then there's context capture. So like test events, configuration changes. So right now we're using InfoPave, I guess, as the online platform for people to download MnROAD data without going through us. Right now, there's only one environmental sensor data set on there. It's thermocouple data, but it's only hourly. All the other sensors have not been put on yet for environmental sensor data. And there's quite a bit of data. And I don't know if we're going to put more on. Right now, we're sort of in a transition period where we're thinking we want to build future dashboard that we own and operate ourselves. So that way we can directly connect it to the database, so that then it'll just, every time the data gets loaded into the database, the dashboard will get updated. And then people, like during construction, people would be able to get the data a lot quicker for writing reports. So they could just download everything. So as I said earlier, we're improving right now is we're trying to improve the catalog metadata. We're going to make it fair to line. I'll talk about that in a little bit. What does that mean? We're going to standardize formats and naming conventions. And then we're also going to do better documentation and user support. And this is all going to help us move towards having the ability to create web interfaces. So we can search, filter, preview, and then do guided downloads. And then as part of this process, we're also going to automate our loader a lot better. And then we're going to improve quality assurance and quality control checks. So we're going to add more of them onto our data, so that way there's a quality check, I guess, like there'll be like a value added to that data in another column. So then you can be reassured that the data is high quality. So this is the, I guess, the future experience, or FAIR. So FAIR just stands for findable, accessible, interoperable, and reusable. And so findable just means like you can search and find the data. Accessible just means I can get self-service downloads, like if it's on a dashboard. Interoperable means it's just consistent across all the data sets, they're all connected. And then reusable means that people can keep reusing it over and over again for different types of studies. Also, if people get data from here, they can use the MnROAD IDs that are attached with those samples, so that way it's a lot easier for us to figure out when people do publications, that we can connect that to a study. Because we're also trying to add a table that connects different papers and reports to different test sections. So, the value to MnDOT and NRRA is we're trying to move towards the direction where we can do faster analysis and better decisions. We want to reduce the rework and duplicated effort. We also want to gain stronger collaboration with partners, both internally within MnDOT and nationally as well. And then we want to have more impact from past and ongoing investments. So how can you all, I guess, help us as well as us help ourselves? It's share priority research needs and data use cases. Like, what data are you actually asking for, or what would you be interested in asking for? Not many people look at the database that often or go really deep dive into it. They don't know what's there. There's a lot of useful data in it. It's just very underutilized right now. I guess, and going along with that, use MnROAD static curated data sets, section IDs, and metadata standards. So like, if you use this data, it would really help, because when you produce, I guess, papers, or you produce analysis of the results, it would help connect it back to what we're putting into it. And then I guess eventually, as we're producing our dashboard, we would probably are going to want some tool pilots or dashboard testers. So, and then as part of that, we're going to move in after the dashboard, where we want to move into like collaborating on AI, QC, and analytics enhancements. So just want to say thank you. That's the end of my presentation.
Morning, everyone. Before we start with the Geotech talks, I want to acknowledge one of my coworkers, Terry Baldridge. This is his 40-year anniversary of working at MnDOT. So if you don't know, he's a Pavement Foundation's engineer, or the Burnham-based spec owner for MnDOT, and he was a past chair for the Geotech team. So I learned a lot from him. Appreciate all the work, all discussions, good and bad, all the argument we'll have throughout 7 years at MnDOT. I'm hoping to have 2 more years, and thank you for making me a more practical engineer. I'm very theoretical, very volume oriented. These guys have been pushing me to be more practical. So I appreciate it. Thank you very much. Now I'm gonna have a cool talks. I'm very excited about these 2 talks because they have a lot of modeling component on it. Again, this is a lot of good geomechanical advanced modeling for these 2 upcoming presentations. Majid is one of the experts on saturated soil mechanics nationally and internationally. He currently chairs the ASE Institute on Saturated Soil Mechanics Committee. So I think you guys are for a treat. And I'm sorry you have only 15 minutes. Majid. Okay. Oh, sorry, you are.
Okay, good morning. Hello. So the purpose of this presentation, in 10 to 15 minutes, I try to update the work that we have been doing with the help of Raul and Ben and NRRA group on the flooded pavement app, which we started like 4 or 5 years ago. We've gone through several modeling and iteration pieces, and the goal is to update where we are. And the title was lesson learned, so what we learn, what we need, right? So I have a little bit of project review if you are not familiar with the whole idea, and then some tasks as part of this phase 2, what we have been doing. So if you are not familiar, this flooded pavement app really started 4 or 5 years ago at the early NRRA. We're talking about like the research need and everything. We said, okay, we need a tool to really help us for decision making when we open the road after flooding, and depending on the type of traffic, or even looking forward, depending on the precipitation scenarios, what type of maintenance we need. So there's a website we have that we are hosting, the current version, we call it PaveSafe. The idea of the title came from just a grad student who can develop the first version, PaveSafe. It's called PaveSafe. The QR code brings you to the website, and basically there are publications there and everything related to most network phase one. You can download them. So the version 1 is already available. The goal was basically a decision platform for flooded roads and also help us to predict the performance of. The focus was mostly on flexible pavement, for the different loading and climatic scenarios, and also ultimately to predict the safe traffic patterns. The project really, the first phase was a lot of system analysis. We wanted to see what are the key influencers in this whole analysis, and we did the system dynamics analysis, quite a bit of time on that. Then we did the different types of single variable, multivariate sensitivity analysis to identify and rank the important parameters impacting the response of the pavement after flooding and during flooding. And that led us to the version 1 of PaveSafe app. And basically, it's designed to be single but mechanistic. So there are lots of mechanistic modeling behind the scene, but the face of it is pretty simple. Just put the pavement information, the structure, the geotechnical information, your precipitation scenario, you have your traffic type, and you can define the threshold and say, okay, it's open for traffic after 24 hours, after 48 hours, and flooding and rain. And maybe you have 2 consecutive rain scenarios back to back. So all of that can be modeled. So I'm not going into detail of the modeling, piece. I just wanted to introduce, if you are not familiar, that's how the software works. So then we got the phase 2, which the focus was mostly on enhancing and computationally enhancing the model, the application, and also using the available data to validate to see if really the performance is good. There were different tasks. We are almost toward the end of this phase 2 as well. The experimental and numerical part, we wanted to be robust, so it took a little bit longer time. So we are hoping that sometimes end of summer, we are done with this project, and the actual platform for the version 2 is already ready. Just wait for the final numerical model, independent numerical model to finish so we can do final validation and release it. Otherwise, the actual platform for version 2 is ready for like a few months. So we started with phase 2, just a quick review. We did a survey from the body that is going to use the app. What are the needs of improvement for the previous version? We got data, and with our tab meeting and other experts we said, and so we come up with a verification and validation plans, like what are the things that we need to do, validate, and we broke it down to a set of physical model testing and also numerical modeling. Our testing started with typical resilient modulus testing, and we targeted 4 points at optimum, between optimum and fully saturated, and then 1 fully saturated, which is the flooded, and like a almost saturated, nearly saturated soil. We tested it for fine sand, silty sand, silt, and clay. Clay was from MnROAD section, and we wanted to see how the resilient modulus. This is probably other people have done, but we wanted to have a good idea in our model, and we could see that as the degree of saturation gets nearly saturated resilient modulus drop quickly. That's intuitive, and I'm sure a lot of other researchers. The part that took a lot of time, we wanted to do a more physical model testing. We built a setup at University of New Hampshire, and we wanted to not only load and simulate a traffic scenario, but we have good instrumentation, we can capture the response, right? And the setup basically, it's a pit, we have soil in it, and and the bottom is, we have a network, so we can drain and insert water from the bottom and control the water table. And basically, there are lots of instrumentation in and out. This is the actual hydraulic actuator that we control. We can apply any type of transient load that we want. So there are different types of scenario. The load sensor we have, the two things, like there are moisture sensors and also laser transducer at the surface to capture the surface profile. But we also had the pressure sensors. We wanted to see how the pressure profile within the soil is. That's important. And also we have pore pressure sensors for the tests that are fully saturated, how the pore water pressure change because of dynamic loading, and that could cause liquefaction in the soil. So these are the sensors we have. This part, the task is complete. The report is on the NRRA website. If someone is interested to get more in detail of like how the results are, I just review some of the results. Basically, we did about 32 relatively large scale physical model tests on sand and clay. And we did it at dry, optimum compacted, off of dry, fully saturated, and we control the water table and salt test to see if the water table moves. So we apply a half sine cycle with this rest time between to replicate traffic, and we measure the surface settlement, vertical settlement, the stress propagation, pore water pressure, all of them. A few of the results, for example, this is the results of one of the pressure sensors. Each box is for different degrees of saturation at the shallow depth. On the left side, these are all the input, the envelope of cycles. We apply 105 cycles of pressure, but if you take the envelope, the peak of those, so there is a time because it densifies at the top, it takes time to get to that 100 kilopascal. But interestingly, for different degree of saturation, basically what the sensor measured is either higher or lower, and that's because of the stiffness of the soil. You may have a lot of relaxation in the soil, or you may have a stress concentration in sand and different materials different on the. It is also discussed if you go to a soil mechanics book, if you have a rigid foundation, flexible foundation, clay, sand, the stress concentration and the middle and the edge are different. So this is a traditional soil mechanics that we taught in all the classes. We had also the settlements, and basically we track the settlement of that load platform or foundation, and we could, based on that, get the elastic component on each cycle to get some resilient stiffness and also the plastic deformation that's accumulated. And with that, we could define two types of stiffness, the secant stiffness, which is basically considering all the deformation, and the so-called resilient stiffness is just, and then that how that changes with respect to the porosity and basically the suction level or the representation of degree of saturation. And it makes sense that as you increase your suction from left to right, you have more stiffness, which obviously the source is stiffer. And we defined it about, the suction we are representing is like for half a radius in the surface near the foundation. The other piece that we try to understand is the surface profile of the loading, because we have this laser transducer across the surface. As we load, we could match or care fit these deformation profile. Now we could see how that profile changes based on different porosity, different degree of saturation. So that's another piece. Again, I'm not going to do all of this. I just want to show what's in there. If you're interested, it's pretty, just the experimental part is like 200-300 pages of document if you want to go read the document. And then one other interesting piece that we were really looking into was the pore pressure sensor data. And we have pore pressure sensor right underneath on the side. There are interesting things we observe. Of course, we expect that as you load it, the pore pressure goes up, but when there's an unloading phase, there is a movement of water. That means we reduce the pore pressure as well. And that's something we are also seeing in the numerical part. And that's really hard in numerical model. So that's one piece that we are working. And then also, for example, if we define the pore water pressure ratio of 1, and then this is the saturated one, we can see there are parts that on the very shallow, like half the R being the radius on the top, we have parts that this soil is liquefied. And if you are in geotech, you know, for liquefaction is basically use your shear strength. And so that's not, so that's the experimental part, trying to be on time. So then that's done, the report is there. The next piece is the numerical modeling. We are using Praxis, But because we are doing a lot of different models, the mesh is big and everything, we take a lot of time to develop a Python coupled Praxis system. So we basically don't need to open Praxis, just you're modeling everything and then analysis with Python. And we, our grad student Nizar, is also having a poster there, so he spent quite a lot of time developing this platform. So that way our sensitivity analysis become easier. And then we work on different constitutive model. There are two hardening model, basically in Praxis. The hardening is small. It seems to be work better because it can capture the initial deformation. Hardening model jump into the large deformation. We couldn't see the hardening behavior at the beginning, and then we use UPC 3D for the liquefaction piece, the saturated model, which better capture the effective stress-based analysis. We did the more Coulomb just for the starter and also comparison. And there was a lot of challenge because the deformation is large at the very beginning. So it passes the yield point of the soil, and then you really, every time you load it, you get a lot of plastic deformation. So we needed to play with the soil strength properties a little bit so we can trigger the hardening every time. So that took a lot of time. So we got some modified system that really now, if you look at, for example, the hardening soil, which is the green, and hardening small, so if the hardening soil jump into the large formation, we couldn't get a nice transition. So there are pieces of, so this report will be very interesting. There are lots of basically geotechnical or geomechanics modeling in there. We are very excited about the results. So now we can capture the hardening response, and we have more permanent deformation at the beginning than comparing to the last cycle. So after that, we do the sensitivity analysis. This is ongoing. Hopefully within a month or something, we'll have the report for the review by a team. So the PaveSafe version 2, as I said, the platform is ready. The goal was to basically enhance the what we have and the user interface, and also a lot of basically validation. So we will validate based on the numerical and experimental part we have. And the main validation will be the field. We did a lot of search across the country. There is not a well-instrumented system that we could use to validate. So we have the physical model, we have the numerical, those are good validation, but it's still not. So this is a run of the new version of the app. It's just show different components, and we did a lot of different pieces in it. And basically, the geotech piece, the structure piece, the scenarios, they're all more advanced. Computational is much more faster, and then you can put any scenario precipitation you want. We added even loading scenarios that are custom. You can put your loading scenario, you can put FWT, all of that. So these are, and then at the end, it tells you the road closure, caution should be closed, all of them. And basically, as I said, the platform is ready. We're just waiting for the final validation, and we'll hopefully release it sometime end of summer. So lesson learned, just because the session is lesson learned. There are lots of fundamental and practical knowledge developed just for understanding the response. And these are available in publications, reports. If you are interested in this area, I encourage. You have the app, that's the product, right? It's good to have a research that ends up in a product. The version 1, version 2 coming. And then lesson learned was we need a control field validation system. And the flooded road section is perfect. I gave the lesson learned to AI and gave me this. So the flooded road section that you are going to see hopefully will provide a good tool for not just this research, but any other person who are interested in investigate it. And it's interesting that the UNH team doing the analysis, they have a coffee. They even think that when you do modeling, you need coffee. So, and I'm available throughout. If you have questions about the app or any other thing, I'm happy to answer.
What we have,
research on the water repellency technologies and the section that was built at NRRA. Check if it works or not. And have two researchers from Michigan State, Qasim and Mohammad. And I know I don't have probably check time with Qasim because Qasim has a military background. I think you're a colonel, right?
No.
Major. So I think he's gonna be.
Thank you so much. Thank
you.
That puts me under more pressure, I guess. Yeah.
Okay, guys. Hello everyone. Good morning. My name is Qasim Zulfiqar, and I am a Ph.D. student at Michigan State University. And I today, along with my colleague here, Al-Khateeb, who is also a Ph.D. student at MSU, will be presenting to you our research titled "Improving Moisture Resistance of Pavement Foundation System in Engineered Water Repellency." And via engineered water repellency. And our research team includes, along with both of us, we have Dr. Adriana and Dr. John Daniels from University of North Carolina, Charlotte, and Dr. Bora, who is the PI, along with Dr. Kareem Shetty, acting in an advisor role from MSU. So the presentation is, looks like this, the outline. I will start with the background, some information about EWR, engineered water repellency, and some goals and objectives, and then comes the meat of the presentation, that is the modeling, and in the end, lesson done. So for the frost action, some background, my colleague here yesterday, Majid, had elaborated upon the frost action and the damages due to frost action in details while he was presenting within geotextile presentation. So as he said, frost action causes a lot of damages in the pavement system, and one of the major contribution towards increased moisture in the system comes from the migration of water from the unfrozen soil layers towards the frozen soil layers. And that capillary action happens due to a combination of different chemical and physical processes. And these are like some of the pictures that I have, damages due to frost heave, and the resulting damages due to thaw weakening during the summer seasons. Now, he also mentioned about some of the frost heave triggering points. Mainly, they are like sub-freezing temperatures, frost-susceptible soils, and the continuous water supply. Now, the present-day research, and there are like different procedures in place that are dealing with each element individually in order to address or mitigate the frost heave damages. But in our case, what we are looking at is the continuous water supply from the unfrozen layers towards the frozen layer. And we do that with the application of organosilane chemical, and that is sprayed on the soil layer, which end up acting as a capillary barrier for the water, to stop the capillary movement of water from the towards the top of the pavement layers. And we call it the complete mechanism as engineered water repellency. So as I said, we have to treat the frost susceptible soils with the organosilane chemicals. How the chemistry works, I will just briefly tell you about it. So we have this silicon-oxygen-silicon bond formed once the organosilane reacts with the surface of the soil layer, and it forms a dense, thin, water protective layer, which makes the layer hydrophobic. And with that, once we applied that in the field, it results in controlling the capillary action of the water from the unfrozen soil layers towards the frozen soil layers. So with that, I come to the goal of our presentation, that is to evaluate the use of organosilane to control water and increase the overall pavement performance. And then we have like different objectives with this goal in mind, starting with the soil characterization. So as I mentioned, this is a silicon-oxygen-silicon bond. So it is important for the soil to have silica-rich chemistry. So what we did, since these sections were being constructed in the MnROAD testing facility, so we collected the soil from the testing site, and we ran like some XRD or some structural analysis, and we found out that the soil is indeed silica rich. And then after that, our colleagues at university in North Carolina, Charlotte, they ran some physics-based models in order to come up with an optimized depth for the application of the EWR treatment. Now, they came up with the number of 3.94 feet, and it is important to note here that this number is not a design depth that we are recommending to the users, but it was the number that we had for our construction of the testing sections, test sections at the MnROAD facility. So we went ahead with that number and constructed two cells, a control section and a treated section at the MnROAD facility. Both these sections had class 5 Q aggregate as a base layer. Those sections had a combination of different sensors, moisture sensor, metric potential sensors, along with the shape arrays. And the treated section had 3 layers of EWR, application for organosilane chemical, at a 3 feet, 3.5 feet, and the number that we have, 3.94 feet, the 4 feet, the maximum depth. So we had these cells, and after 2 to 3 months, we had a small setback where we observed some failure in the control section, which has nothing to do with the EWR application. There were like some side reasons with that, and that is a separate topic. We did a detailed forensic analysis on that. It is available as part of the task report of this project. And but yeah, we went ahead after a few months and designed, went ahead with a new design for the control in the treated section, where we had a large stone aggregate and the drainable stable base. And we tried to not disturb the sensors and the EWR layer much. So the configuration for that remains the same. And with that, we started collecting measurements from the moisture sensors, from the temperature sensors, and then we went ahead with the modeling part, which will be explained by my colleague here. Next one.
Okay, good morning, everybody. Hear me? Okay. So good morning, everybody. I'm Mohammad, working with the modeling and the field analysis data for the project, for the water repellency project. And I will start elaborating just the main ideas of the modeling because it has many details and complex boundary conditions that I don't have, unfortunately, time to elaborate everything. But feel free to reach out to me after the presentation so I can elaborate everything. So for the modeling part, there is our main goal, which is to develop thermohydraulic mechanical modeling for a cross action for MnROAD that helps them to understand what's going on in the field and how they can treat or mitigate the frost heave in MnROAD. For this project with EWR, but after validating our model, they can use it for different strategies that will help them to mitigate the frost heave. So I have mainly 5 stages for the modeling, starting from A to Z. So we started by looking for the literature, what's the model that can we rely on, modeling field analysis, which has many things to deal with. So after looking, we found that Vrtis 2D provide thermohydraulic mechanical analysis, since you have temperature gradient, water migration, you have heave and settlement. So Vrtis 2D we selected based on the literature we read with a frozen soil model. Then we started, because we want reliable model, we started with lab-driven properties. So we went to the lab testing different temperature, thermal properties, hydraulic properties, mechanical properties, and coupled thermal hydraulic mechanical properties. Like we did unconfined compressive strength and frozen soil, like many details. Unfortunately, we didn't have time to discuss in detail. Then we will start with a validation with the model at lab scale to make sure we understand first that, okay, is there something we can do at lab scale to understand the model more, frost heave more? Then we went back to the field scale, like we have different sensors in the field. And before the modeling, there was like a vague of what's going on with the field because we have different sensors. So the model that we validated already answers the question that we were looking for from the field. So finally, we did the sensitivity analysis. It's still going, but I will share with you those steps today. So for the lab scale, you can see here 5 cases. 5 cases. Case 0 is the control section at the lab scale for frost heave testing, and we have 3 cases applied with EWR spray rates, as you see, with different concentration, and all of these selected based on what they applied in the field. So all of them high water repellent zone. And the case 4, which is a closed water source, to compare if the EWR really blocks the water migration as we closing the water source. And here is the boundary conditions for the model. So in this slide, you can see I'm just wrapping up the measured and the predicted from model and the field. You can see case 0 has the highest frost heave, but all other cases showing a minimal about 0.05 inches, about 90% reduction in the lab, which is a good indication that you really mitigate the frost heave based on the model and based on the lab scale results. Now for the field, it's a little bit tricky. How do I select those geometry and boundary conditions? But we have sensors, we have some analytical solution to find what's the depth actually we need to model based on where is the temperature constant and doesn't affect by the seasonal. So we have much detail. We are writing the report for this, so soon will be published. Yeah, so we started with the modeling and we feeded the model with actual data. Like this is temperature profile at the top of the subgrade based on sensor installed there. And we have water table fluctuation during the year to apply in the model. So finally, here is what the model answers. So you can see here, sorry for the busy graph, but it should be because it's coupled, so we have different things. So first graph is showing the unfrozen volumetric water content, which is measured by the sensor installed, and what's the model give us. The interesting idea that the frost action, it's water migration, so you are thinking that you should have more water in the freezing period, but the sensor was showing it is a reduction. So that's because of a limitation that the sensor showing just reading the liquid water content, not the total water content. In other words, the ice and the liquid. So the model answered it, and you can see the temperature profile for this depth in the control section. And if you look at the last graph, you can see the total volumetric water content that's produced by the model. It's showing that here is the water that migrated to this sensor depth. So I have similar scenarios for different depths, but I'm just showing those depths, the last and the first depth, to show you that you have the tool to understand different scenarios for the model. And here is the treated section with the EWR. The same thing, you have the same scenario that you can now see why like for example, the deformation was not showing a big difference in the field readings for the shape array. But now the model really answers you for all these questions. So lastly, what's predicted in the model, it's showing that if you apply at those design depth, you will have frost heave reduction about 50%, but the interesting idea that it reduces differential frost heave. So now you are damaging more the pavement. So should be cautious. The mechanistic design of EWR is very important to have the advantage of it. So we did sensitivity analysis, for example, we raise up the AWR 1 feet was showing now 70% reduction, but still we have differential frost heave. So what's the solution? We found the solution is to laterally extend the AWR after the pavement shoulders. So now you will have about 90% reduction in frost heave, but also you can see it's minimal differential frost heave produced. So so for the lessons there, EWR really works, yeah. But it's a tricky a little bit. So you should design it carefully. And the mechanistic design is more important, like how many layers, how lateral extent you should. And as I said, improper EWR design could use differential frost heave. And lastly, lateral water movement is important in frost heave because once we block the water from the bottom, the water was beating up like above the AWR layers. Yeah. So and finally, the optimal MnROAD configuration based on the suggestion from the model is 2 feet depth with 4 feet horizontal extension to achieve the high frost heave reduction. And finally, I want to thank the TAP members for their valuable support and really appreciate it and see you next week in the TAP presentation to provide more details. So yeah, here are the references for you and thank you. Any questions?
Thank you, Mohammad. I think to show that advanced modeling pays off, so I appreciate that. I also want to thank Majid and the candidate for really, we suggested strongly to use Practice 2D. And the reason why is because we have access to that at the research section. and the geotech section, the use of these tools. So we were thinking about implementation behind you guys will give me. Anyway, thank you for being flexible on using the tools that we have available so we can look into implementing some of these tools. Thank you.
Good morning. I pretend I'm the moderator, and I introduce myself here. My name is Zhanping from Michigan Tech, and I have a large team here in the audience here. And I included in Ghayoomi, Kobe, and from Mohammad, Mangu, and also I adopted another member here, Tyler Hunt. I did not inform him, so Tyler there. So the reason I put Tyler here, because for this project, there is a really major construction going on, and we need the money to do construction. So Tyler actually worked really hard to get money to build the road in Michigan. So that is something I really adopted him. I did not have him yet. So I'll talk with Tyler after this. All right. So what we are trying to do is talking about a hot rubber chip seal to survive the wet frozen environment. That is really, initially my plan was going to build this in MnROAD and also somewhere in Minnesota, but eventually we figured out a nice site in Michigan. All right. We are going to talk about the background. So first thing is because I personally really love to see seal coating work for chip seal. Which really in Minnesota, we have a lot of those work ongoing. A lot of cities, counties are using a seal coat. And then in 2017, of course, up to 2017, Michigan Tech has been actively working with a lot of cities and counties to deal with the chip seal. So that's something give us a lot more confidence to see how really we can make the technology move forward. And then, of course, later on in Michigan, we work with some government agencies, like a lot of counties, cities, to build some chip seal. But the chip seal we're using is not using emulsions. Instead, use a hot rubber asphalt. Right. That is something really make us. We build a lot of miles of roads. So, for example, the last column line here says, like, instead of using something like a CRS2P or CRS10 sort of emulsions, we use hot rubber asphalt in Michigan. So far, we built actually over 300 lane miles of hot rubber asphalt in Michigan. So most of those are actually in county roads or city roads. So today we are going to report some work we did with MnROAD, so under Tyler's leadership. So that is something we are going to review with that in just a second. So we find out this hot rubber chip seal has a lot of potential, really, because not only from the field performance and also from the laboratory performance, we see that it's really great thing to build. So the hot rubber chip seal, we see that it can reduce the premature stripping and also extend the pavement life dramatically. So with some kind of well-controlled sections, I think we see the benefits. So right now we are still doing the field monitoring. So under Tyler's leadership. So with that, I'm going to really briefly move to my major objective. So really what we are trying to do is demonstrate the use of hot rubber chip seal to reduce premature stripping and extend the pavement life. And of course, in order to do that one, we also need to construct a lab and field testing for a lot of those data to support our project. So about the chip seal, we know there are a lot of benefits. So these are two pictures here showing the work we did in the past. So of course, one thing we find out, of course, reduce the durability and the maintenance cost in general is going down, and enhance safety. Of course, a lot of other benefits like long-term cost effectiveness. So that is according to some work we did really with counties and cities. So the research work here, of course, major, the report we have here is one is really about literature review. We continue the literature review effort and construct lab testing protocols, and then did the field construction and also have field testing. And right now we are in the final data analysis and prepare the final report at this time. So here is a picture showing how did we prepare the rubber asphalt. So this rubber asphalt facility actually be moved to the asphalt mixture plant So we have that one to prepare this materials in the location here. Of course, you can also ship that one from some distance. So over here, so rubber content added to the liquid is about 22%. Of course, we can run up to 25% in past. So so that really, this kind of asphalt is going to be the high viscosity. Of course, we did a lot of other testing, and I just will show you that in a second. And we also, of course, in the project, we also use some control sections using the conventional emulsions, right? And also, of course, we have the, we also have the special distributor truck, which is spraying the hot rubber asphalt on the site. So you'll see that one in a few minutes. So we also, test the things like, also other asphalt content. For example, for this particular project, we actually have one thing we did was we have done we use the pre-coated asphalt or chips, sorry, pre-coated chips. The asphalt content roughly about 26% or lower. So of course we tried many different things. My first project, very first one, was using 1% of liquid, which turned out to be pretty high, too high. So that's the reason right now we are scaled down to about 26%. And we did a pretty comprehensive lab testing. So including, for example, like the resulted rubber asphalt binder, we did a lot of testing, for example, the viscosity and all the dynamic shear ergonomic testing, all the low temperature performance testing, and so on. And for the emulsions, for the chip seal side. For the chip seal side, we did a lot of other testing. For example, I'm going to show you that one, including the swift testing, surface friction, and of course, the fun testing we did was the strength. So we tested the tensile strength and also the shear strength, both. So we will have that data showing that one just a second. So for example, this is the sweep test. We are trying to make sure there's no aggregate loss after this many cycles of sweeping, and also test the friction, surface friction as well. And one of the testing we did is freestalling testing. So freestalls, 6 hours, you room in temperature, water, soak on water, and then freeze it at minus 18 degrees C for 6 hours, and then thaw it again at 6 hours. So the reason we do this one, because we are going to test the tensile strength and also the shear strength of the chip seal. We want to make sure those materials are going to survive. Because in 2017 study with the NRRA, for that project, we figured out a lot of premature failures eventually really due to the freestyle cycles. If we can make sure the strength-wise here is good enough, so that's an issue maybe resolved. All right, so that is something. Here is the testing protocols we did. This is the bond strength. So the bond strength, we have two parts. One part is tensile strength, tensile bond strength. The other is shear bond strength. Of course, there are other explanation I'm going to have in a second. For example, for this testing, so really what we are trying to do is the chip seal on the top, right? The chip seal on the top. So what we are going to do is just use this to glue our loading head here, and then just pull it. The pull it, basically the load is about 2 inches per minute. And of course, we control the temperature roughly 68 degrees, 70 degrees Fahrenheit temperature. So that's what the testing and going. And then for the shear testing, so shear bond testing, which is similar like this one, but really the key thing is the shear is basically that you can see it's the shear setup is over here. So for either way, so we really, the goal is trying to get the bond strength. So with some of the results, I just want to show you a few results here. For example, here, this curve here, this is 2 inches per minute was testing at 25 degrees C here. So we have the load versus the displacement curve. So of course, a lot of times we could think, we can get the maybe called energy calculation here. We calculate the curve underneath. But the black one really is the rubber asphalt chip seal. The blue one is the emulsions. So we compare the both. So right now, of course, the data I shown here on the very right-hand side. So basically, this one is a tensile strength, tensile bond strength. So what we really have is the peak load divided by the cross-section area of the sample, right? So we usually get to the strength. So this is basically the strength, ongoing. This is the rubber asphalt chip seal, and then this is the no freeze-thaw. This is one freeze-thaw cycles, two freeze-thaw cycles, and then up to like 5 freeze cycles, right? So the other side here is emulsion-based material cycle, chip seal. So of course, for this case here, I only really did was just to compare the tensile bond strength. I did not really, bother with energy. But if you take a look at the energy here, for example, for this case here, the rubber asphalt chip seal, the energy looks like it's going to be like 4 times more than, or at least maybe 3 times more than the chip seal or conventional chip seal with the emulsion-based chip seal. So that really gave us a lot more confidence, of course, how really, why this rubber asphalt chip seal may perform way better than the regular chip seal, right? That is bonded direct tensile. And the other testing I get to mention here is shear bond testing. So the setup is going to look like here. And so again, similarly, the black one is rubber asphalt, and you can see the blue lines here is a conventional emulsion-based chip seal. So again, we can calculate energy here, but really the data here I show you just showing the shear strength and what we did. So of course, this one no freeze-thaw. It's a 1 freeze-thaw cycle, 3 freeze-thaw cycle. This one's 5. This group here is a hot rubber, and this group here is emulsion-based chip seal. All right, those are 2 major tests we did, and then first, we have large amount of testing. A lot of those testing really we somehow take pictures of those samples, and then that is basically called the field, the in-house testing. And then we move to the field. So the test section we built it in Bay County. It's M25. M25. This road, actually the traffic right now is picked up. So it's not really heavy traffic volume roads in Michigan, but it's one of the pretty decent traffic area. So the location-wise, it's really pretty ideal for the construction. So what really happened here, this is the 2-lane road, so roughly about 6.6 miles. So eventually what we find out is this, the first 5.6 miles or so, the condition a little better, and the other 2.6 miles, the condition wasn't, not as good. So the pacer rating per se is very low. And of course, Tyler has those other IRI and all those data. And so we're going to use that much purpose report as well. So what we did here was, and we did the first segments here, in roughly about 5 point some miles here, is using rubber asphalt, right, with coated aggregate chips. And then the last section here, we use, a different design here. So what really happened here, we're trying to just give different combination of strategies that we're using. So here is just the one of the really quick video here showing about the construction we have here. If this thing can show, looks like it's working even though there's no sound, but that's okay. I did use the AI to make some kind of interesting things there, but we don't have to hear that. So the location is it's one of the decent project we did. Of course, like I just mentioned that we built the 300 lane miles already, and this is a part of our plan. So this year to 2026, we're going to have a little more construction ongoing. This is rear truck. So the rear truck actually need to maintain the temperature so that the rubber asphalt can still variable. This is the plant where prepare the coated the aggregate chips. Of course, this is not required, but I think this is a good way to make sure we have good retention of the aggregates. And of course, one key thing here, the asphalt content should be low, should not be that high. And then, of course, in the construction site, you can see we're starting to spray the hot rubber asphalt. So for this road, roughly we are spraying about 0.55 gallon per square yard. So it's pretty thick rubber asphalt. Those are vapors. But of course, the temperature here right now is pretty high. We are also working on to see if we can reduce the temperature. So right now it's pretty much running 400 degrees. This is how really we spray the chips. Of course, You don't want to step your feet on the asphalt. So of course, after the chips is sprayed, and we just do the compaction. So after the chips is spreading, we just do very light compaction. And of course, the construction can be really fast. If we planned this 6 miles of stretch construction, really during the entire construction, just I will say they're very short. If you just come there late, the things are finished already. So of course, last step, you're sweeping, just make sure there's no excessive amount of aggregates. Usually there, we don't really apply too much aggregates here. So that's pretty much the construction. All right, I'm going to click next one. All right, so what we did is after the construction, we also did some other testing. Of course, Tyler is doing other testing, but we did some kind of smaller testing, such as the field pull-off testing. And so after the construction, like 3 days, we did the pull-off testing. It's almost like tensile test, bond strength testing. But of course, the thing is really hard to control every temperature, because whatever temperature we're giving with that day, one is 13 degrees in one spot, and the other spot is 116 or 117 degrees, which is whatever temperature we have. So just measure those strengths. So you can see the pull-off force roughly 220 or 240 something PSI, and then of course we get the average number. So what we have here is that you see hard rubber asphalt, give pretty high numbers here. We do have the conventional asphalt as well. I mean emulsions. Emulsions, for example, here is this one is after 3 months of construction. You can see the emulsion-based one is 77 degrees Fahrenheit. All right, was 332. But under 86 degrees Fahrenheit, the rubber asphalt it was 345. So no matter what, the rubber asphalt still give you a pretty high pull-off force there. That is the pull-off. And of course, we also do some of the really very conventional surface friction testing. And Tyler actually volunteered to use a van and get the speed resistance for us. Thank you for that. So this is data here is provided by Tyler also. So Tyler did was just use a van and get the a lot of data we only show today, only some kind of cracking data. So before the construction, the crack all over the place, so sort of the distribution look like, and then after that one, you can see it reduced the crack dramatically. And we are continuing to look at the data and then trying to get a decent report out here. So with that, of course, we are closely work with Tyler. And with that, I appreciate the effort, NRRA to support the project, and also MnROAD to help this one. So with Tyler is coming up here. So we have a really nice team here, tapped really, including people from different states. So that's all I have. I can Tyler already volunteered to answer any questions or do any give any remarks.
I was supposed to moderate you, and I apologize. So that's.
Oh, I did by myself already.
Up for it now. Anyone have any questions for Dr. Yu?
That's a very good question. So we actually measured those things, yes. I think roughly about 80% or so. Thank you.
Anyone else? Great job. Hope you have one.
Yeah, I'll just got it. Very nice. What do you think is the mechanism of the additional tensile strength, shear strength with the inclusion of the rubber? Is it mostly mechanical? Is the toughness of the rubber intercepting cracks, or do you think that somehow it's a modification of the binder? The rubber's helping the binder decide this mechanical, so like mechanical.
Yeah, it's a really good question. We have not think much about that, but of course, one thing I think mechanical modification probably plays a major role. There might be some chemical mechanical process behind it. So that the strength wise high. So the reason we really have interest to measure that one, because we noticed that there were some premature failures in a lot of roads in Minnesota. So that's what the, in our 2017 research work with the LRB. So we investigated, we find a lot of roads, really the top chips, really easy to get the pop off. So sometimes it's almost like an entire lane or entire wheel path. It's just all the, the chips will disappear off very easily. You can use a screwdriver. I think Paul Nolan is here somewhere. So he and I actually drove along a lot of the roads. We use a screwdriver, easy just to pop up a lot of little chip seals. It's underneath pretty wet. It's almost lose any bounds. There's no bounds. That's the reason we're trying to say, okay, what if we can measure those things? Are there any really what bound stress is meaningful for us? So that's the reason we really right now really focus on the bound stress. But the one thing I thought about the work you did in the past about the disk compactor chips samples. Those are you measure the fracture energy or fracture resistance. That's really something I'm trying to think maybe that is something along the line we should really also look at. Thank you.
Next we have Adriana and Vargas, just going to give an update on the use of recycled materials in pavement preservation. So please take it away.
Thank you. Good morning, everyone. I'm gonna keep mine more of a high-level update here. I knew I was last in this block, so that usually means a race against time. We give a little bit of background here with this project. The idea of using recycled materials seems like every time we have some waste material that we don't know what to do, we want to put it in our asphalt for our roads. And that is the case also when we're thinking about preservation treatment. So we wanted to see the feasibility, first of all, evaluating, well, can we use certain recycled materials, put them into our chip seals, our slurries, our microsurfacing. Also quantify the benefits of doing that. So just economic and performance benefits that we could see if that is the case, and develop a plan for future implementation. As part of this, we did a survey of NRRA agencies, and just a few of the findings. There was multiple questions, but some of the things that I wanted to highlight. Most of the agencies that responded, they're already using recycled materials in their conventional paving applications. So that's about 77%, but only about 55% said that they will use them or have used them in preservation treatment. And once we started looking at the responses, that included things like, well, we've used wrap in a thin overlay, or we have done our hard rubber chip seals. So we wanted to see other types of materials that we could put in there. The primary drivers for doing so for any agency would be mainly cost savings and sustainability benefits. So that was the most important part. And also how the agencies rank, how they would want to use the recycled material. So the top application that they saw was chip seals. So we could do our recycled chip seals, then microsurfacing, and the third one is slurry seals. We did a lid review, and some of the more common types of recycled materials that we found obviously would be wrap, recycled tire rubber, and RAS. So with wrap, that seems to be the low-hanging fruit. It's highly abundant. It can replace up to 100% of the aggregate in our either chip seals or slurry surfacing systems. And some of the preliminary findings saw that there's either similar or better durability, but there are things that you have to be careful with, so maybe requiring more cure time, for example. With the tire rubber, also commercially available. If it's an emulsion, it's a little harder, the process for emulsifying that rubber, but some people have to play with that. They can also be used as an aggregate substitute or like a mineral filler or something like that. It helps with aggregate retention. It helps with cracking resistance. It could be a little bit challenging during construction though. And finally, for the shingles also, they're available, but there's limited data, especially for any preservation applications. It could be that we use them in a slurry surfacing system again, like some sort of mineral filler. They showed lower cohesion, but there wasn't something where you could just replace all of your aggregate with shingles. It was somewhat of a blend. Some of the variants that we saw from that survey, well, most of all, that lack of performance data, a lack of design guidelines. So all of the design methods that are already available, they have been developed based on virgin materials. Also, we don't really have our QC or QA protocols and material procurement. So with our lit review, we saw things that were like broken glass or some waste concrete that's been removed and things like that. But when you look at it, well, how feasible it is to get that actually now and use it on a project, does it require a lot more processing? Is it already available? So looking at what we have done so far and with our experimental plan and all of that, we decided to, for now, focus mainly on wrap and recycled tire rubber, based again on availability, preliminary performance data, and how easy it would be to just go and implement in the next step. So we, for each of the treatments, again, chip seal, microsurfacing, slurry seal, we were doing designs with virgin materials and then a recycled design, or up to 2 recycled designs using the AASHTO protocols that were recently adopted. Again, this is all developed based on virgin materials, so we don't really know how well that's gonna reflect the use of a recycled material. So with that in mind, we're also conducting additional performance testing, just to evaluate that impact of that recycled material on treatment durability. That includes 3-wheel polishing device and then performing our friction and texture measurements. We're doing the sweep test, which is not necessarily a part of the chip seal design, but it's an additional test that's available. And we also have a flexural tension test for the slurry surfacing systems. So looking into our 100% wrap chip seals, do they require more or less emulsion? Well, the question is, it depends on the wrap and it depends on the virgin aggregate that you're comparing it to. And a lot of that depends also on, well, what's your gradation, what's your material properties. So things like the loose unit weight, your specific gravities, all of that comes into play when you do that. But if you run this through your conventional AASHTO design, you will get different answers in there. So nothing really clear in there. We ran 100%, again, wrap chip seals, and we did our sweep testing. What we saw is normally we'll have similar or better chip retention with the wrap. It was pretty low, our loss of material anyway. I'm not much of a fan of the sweep test. It uses a predetermined amount of emulsion, so it's not really reflecting your material proportioning. But nonetheless, it's the test that's standardized and it's available, so we ran it and saw good results if we're using the 100% wrap. So what else could we do with our chip seals? We have seen that 100% replacement works. Some agencies already do this. So we started to look into recycle tire rubber chip seals. So trying to replace some or all of the aggregate with recycled tire rubber. I've been talking with a supplier, a rubber supplier, and they do have -1 inch material that is available. The thing here is that it's pretty elongated. So it is about 1/2 inch wide, but then about 1 inch long. And that is obviously not what we want for chip seals. Chip seals are looking for more of a cubical type of material. So they said that they could further process this, maybe run it again through another shredder. And they're gonna try to give us a material that's more like a 3/8 of an inch, more cubical particles. They mentioned that they have a local agency in Tennessee that is interested in doing this. So it's something that, yes, it could get some traction in there. So we're working to look at what this will do. Advantages, potential advantages that we have seen from our lit review, and some people that have tried this, it's less noisy and also it has good retention. So maybe something like in a residential area or something like that. For our microsurfacing designs, if you're not very familiar with the design process, there's some pieces here that are key in there. So we run our mix times to make sure that the material is workable. If you're doing this in the field, everything gets mixed in the machine and then placed on the road very quickly. So you want to make sure that that's not breaking ahead of time or anything. But we were able to get our 100% wrap designs and all meeting that 120 seconds of mix time. That's the requirement. We ended up using 1% cement with our mixes. Then for our cohesion, that helps us look into cure times and will we be able to open the road up for traffic in a timely manner. We saw that our wrap mixes had slightly higher torque, which is good. They all met the requirements, so that's not a problem. That was easy to meet. Then we moved on to the wet track abrasion test and loaded wheel test. So we want to have a balance between how much emulsion you need to pay your aggregate, but that the mix doesn't bleed or gets like rotting, things like that. So with both of our virgin aggregate and wrap mixes, we were able to meet the 1 hour soak requirement easily. We used a range of emulsion from 11% to 14%. And then when we moved on to the 6-day soak samples, that's when we started to see more differences. So the wrap was still meeting all of the criteria, but then the virgin aggregate would not meet at the lower binder levels or lower emulsion levels. So that what that means is potentially we could use less binder if we're using a wrap. The other thing was going to the loaded wheel test. So this is to see, again, what's your maximum binder content. And there was no problem meeting the lateral displacement requirements. All mixes were under 5%. But then for the sand adhesion, which is the potential for bleeding, or tells us about the potential for bleeding, the wrap mix could not meet the requirement, even going as low as 12% emulsion. So we're looking into getting some additional samples and see if we can go any lower, but there's only so much lower than you can go. So that's just telling us that there's an increased potential of bleeding, even at lower emulsion contents. More than that, we have heard concerns that, okay, well, at high temperatures, that wrap may become activated, to put it that way. So when we're using wrap in our surface treatments, it's not the same as when we're doing with hot mix. We're not thinking about blending or things like that, but we do have to acknowledge that high temperatures, that binder and the wrap may softer and somehow affect performance. So we ran the loaded wheel test at high temperature at 50 degrees, just to see what would happen. And we definitely saw much more deformation and displacement with our wrap samples at the same asphalt content. So again, it could be a concern. This is not necessarily part of the design, but we tried it just to see if there was some susceptibility in there. And we thought, well, maybe we can try a 50-50 blend. And that way we're still using some recycled materials, but more effectively and without any performance concerns. So we've been working on that 50-50 blend. We're using 12% emulsion, 1% cement here for this samples of cohesion. Everything's meeting the requirements so far, so that's good. And we have some testing underway with the wet track abrasion. We completed the 1 hour soak results. Everything is well under that maximum limit. The 6-day soak samples are soaking right now, so I don't have the data, but we'll see. Hopefully, it seems promising that we can at least use a portion of wrap to replace that aggregate. So some of the work that's coming up and we are trying to complete, do the same thing for our slurry seal, start with 100% wrap designs and see if that works or if we need to do a blend. We are also considering using rubber as our mineral filler in there in our slurry seal and perform the additional testing part of it. Now, the main challenge, and I think the main takeaway that I personally have taken from this is that timing is everything when you're working with asphalt emulsions. So one thing that we ran into is we're working with materials, our aggregates and our wrap, for example, for the microsurfacing, we're all coming from Ohio, and we got the emulsion from Ohio as well that's formulated that we know works well with those materials. All that's really good until construction season ended and there was no more emulsion production. So we kind of stalled there for a while. We had been waiting and they just restarted production of the emulsion couple of weeks ago. So as soon as they had it, we got some more emulsion sent our way, and now we're working full steam ahead to try to finish all of that. But that's very challenging because with emulsions, they have a limited shelf life. You can't just stockpile a bunch of it and try to use it. It'll go bad at some point. So trying to depend on people to provide those materials and us being able to get the workflow going. But I think we got it on a roll, and things are looking much better, and we're trying to catch up. But from what we have seen, there is potential to use our recycled materials. What we're trying to develop is some sort of framework so that if in the future you think you want to use whatever else new that you want to incorporate, this is the process that is what you want to do and follow to be able to evaluate that and see if it's feasible or not. And with that, I think we just got caught up. Thank you.
Any questions?
Yes.
A very interesting question, the interesting presentation, all right? You mentioned about the rubber, the chips you said the -1 inch of chips, rubber chips.
Yes.
Is that, is that going to work well, is that project ongoing already? That's one small question. And the other thing, in case you need emulsions in wintertime, we can produce a few gallons for you.
Thank you. Appreciate that. Yeah, with the chip seal, we'll see the -1 inch is what they have available. And as you can see, it's kind of like mulch type of material. We definitely don't want to use that as it is right now. So the supplier is trying to work with us to get us something that's resembling more what we will use for a chip seal aggregate. But they did mention that, yes, there are agencies that are interested in trying this out. I guess, yeah, less noisy, maybe smoother, better ride. Yeah.
Probably use super glue.
I know. Yep. Agreed.
I have one for you, Adriana. Was the biggest from your survey, was the biggest feedback about bleeding, flushing? Was that the biggest concerns? With the use of recycled materials?
Yes.
Specifically, the use of microsurfacing?
Yes. And I think that goes back to the need of, well, do we use the same design process and the same standards as we use for our virgin materials, or do we have to adjust that? And that's part of what we're trying to look into for now. But that was the main concern. If it seems that there's no problems going the other way, like there's no aggregate loss or anything, it's more of the bleeding and flushing side of it.
All right, thank you, Adriana.
Okay, good morning. Well, those of you who were here yesterday, you should already know me by now. So Michael Johnson, I'm with MnROAD, and I am the interim ICT chair. Just a reminder, that position is still open for nominations. So there's still time. If you haven't had your chance to provide some interest, but and you will have the full support of NRRA and MnROAD, obviously. So I labeled my presentation Intelligent Construction Technology Team Update, but I guess I do want to get into that just a little bit more. I'm going to be touching on the MDMS, the Veda enhancements, and also the DPS pooled fund. So there's some very important non-destructive testing topics which Soheil will be talking about. So not a full update, but a handful of these items. So just a reminder, Mike's presentation earlier did touch on the NRRA Phase 3. So the Veda enhancements are included in the NRRA Phase 3. Uh-oh. I didn't touch anything. Okay, we're back.
So we were also with George and Amanda and a few other folks that were discussing Veda. So hopefully that does sound familiar. As George did say, we are working to transition from a desktop version to a web-based version. And I guess okay, I'm not going to stand there maybe. Just a reminder that the desktop version supports intelligent compaction, paper mount, thermal profiling, and the DPS. So I do want to touch again the MDMS updates. Remember, that's the expanded form of e-ticketing. So as George mentioned, we are doing some testing. So we're working on some receiving exchange data. So what happens is we have a vendor that has e-ticketing MDMS system. They're AASHTO compliant, and then we can receive that data into Veda Center. So again, any vendor, AASHTO compliant, they'll work with the Transtech group. There is just a little bit of the reason why we're doing this is to work on the APIs so that that data does make it through the exchange and it does show up correctly. So there's a little bit of testing. We have been doing that at MnDOT, and we hope to expand that out to several more vendors, more projects, and then hopefully some other states later this season. Also to note that the goal is to do structural concrete data as well, in addition to bituminous. I guess let me just throw out another note that there was a big effort to develop the AASHTO standard for MDMS. And remember that that's a big, broad list of information that could be useful, but remember that's kind of an a la carte system for each individual state that decides what's important to them. They can pick and choose those items that are important to them, and then use it for MDMS. But that being said, so as I said, it's kind of a beta version that we're testing out right now. So pretty limited just to MnDOT currently. And then hopefully we'll expand that out to more projects and also other states. That being said, there are a number of enhancements still in the Veda Center that we're working on. And as we get more states involved, hopefully that encourages folks to come up with other wish list items and enhancements that we can add on. But again, just a general list, but more to come. And then also I'm going to move on to the phase 2 of the continuous asphalt mixture compaction assessment using density or dielectric profiling system. So we do have, well, I do kind of want to stand over here. So again, we're moving to the phase 2. So I just wanted to list some of the priorities listed in that pooled fund. So on the research priority side, it's developing, best and worst case conditions for the use of DPS, evaluating improved data collection methods, comparing the DPS to other density measuring devices and technologies, other advancements to analysis techniques, and then uses of the dielectric measurement without converting it to density. So besides the research priorities, we also have implementation and marketing priorities. So on the implementation side, again, developing more training material. There are a number of videos on the pooled fund website available for folks to set up different systems and start analyzing the data, but more training documentation is needed. Again, getting more people trained, and then also getting more pilot projects out there. Updating the DPS AASHTO standard as necessary, and also developing some guidelines and protocols for ghost implementation of DPS. So, and again, with the pooled fund, we'll be supporting, nationally pilot projects and ghost implementation of the use of DPS. So also trying to develop a DPS certification center. And then on the marketing side, and again, pretty typical marketing, but you know, with the pooled funds supporting communication, continuing training, and then promotion of the technology overall. So I'll just give you a little bit of an update on some of the more MnDOT specific parts of this effort. So in 2025, we had 3 roller DPS projects. So those pictures kind of in the top middle, that's an asphalt compaction roller. Down below that is the DPS sensor mounted underneath, right behind the drum. And then this system is integrated into an intelligent compaction system with an onboard display. So this picture on the right is the IC system that the roller operator can see, and it's probably a little small for you, but in a red box, there is a 95 highlighted, which is the estimated density reading from that DPS sensor. So in addition to the 3 roller DPS projects, we also had 3 projects we collected with the 3D DPS system, and then 4 projects with the cart-based DPS systems. So the goal for 2026 is obviously to get a number of more roller DPS projects and then try and compare that side by side. I'll actually have a couple examples of that, of the roller DPS and the cart data, and also DPS ghost implementation of the DPS requirements. So, so just a couple examples here. So on the left is the roller DPS estimated density. On the right is the cart DPS estimated density. So on the right, you can imagine the cart-based system has 3 sensors. It makes multiple passes. So there's a whole lot more information, and some of that is kind of in I guess I'll call it a salt and pepper look to this data here. But some of the overall general trends of decreased dielectric or density was captured with the roller DPS system. So we did you can kind of see the correlation near the top left. The lighter blue with slightly lower densities was captured by the roller DPS system and did correlate well with the cart-based DPS verification. And then also just, roughly in the same spot, but just a little bit further south and east is the green higher density areas again. So correlating well in this instance. Another example where the right side of the lane was more of the blue, slightly lower density readings, and then on the left side again correlated well with the higher green density readings. And then another example where we have just a little bit of blue, mostly green, but then what we also have, which is not in those other examples, is a brighter green, which it's hard to tell on the scale, but that's a even higher density range that just wasn't in those previous examples. So yeah, that's all I had because I wanted to make sure we got to Soheil. So any questions before I move on? MDMS, C-ticketing, IC thermal, DPS, roller DPS. Perfect. Well, it's 2 days in a row you heard about it, so hopefully it's all sinking in now.
Good morning, everybody. It's a pleasure to be here. I have 20 minutes and 2 projects, so I could either talk like the Federal Express man or just give you less information. I decided to go with more high-level information. You don't want to see equations, right? Let's start with the first one. This is a good oldie but goodie. We have a lot of NDT devices and so on and so forth. We know a lot about them, but we deploy a lot of times. We get the data, it comes back, and we don't know what to do with the data. Or we get put the WD in the wrong situation, very thin layer, then we're going to just decipher the information, but we feel disappointed. So this is a lot of money, especially those who don't do it in-house and you're hiring, people what to do. So this is a higher level, just to develop a guideline, what do you expect and can you get it from the devices? And the other side of it is, can we give some recommendations to the manufacturers that, if you do something, and what parameters we use there, so there is no, just a basic recipe, and then you can modify it to your taste and what your culture, so on and so forth. So Jacob Walker is not here from Georgia. He's the running the show over here technically, and then we have Kyle over here, and I have a good record of either retiring people who are on the managing me or just going to another group, take it personally. So I'm glad that guy has taken over from the MnROAD side of it. And then we have a group of signatories over here that are doing the work. So what's the goal of your project? First of all, we are talking about the project level pre-design. So that's the goal to help. So our goal is what are the best tools for the pre-design survey and how to use it, as I discussed. And decide what entity to use, when to do it. And if you look at the objectives, is first, if you're looking for the defects, the pre-design, what are the extent of the defect, and how defective it has to be, so that you can find it. And then the next one, if you're doing back calculation and all the good stuff that you're doing, how good are you doing? Because, you just go through a non-unique process, and are you getting the strains that you are seeing in the field, so on and so forth. So, and that's what we do. So we had 7 tasks. Some of them were not technical, like you omitted over here. The main one that we're going to do that we put a technical advisory board together. That was the first task. That was technical, so that we can get feedback. Documentation of knowledge, strengths and weaknesses and limitations. Obvious, but part of that, we sent a survey out, and we were lucky enough. Jacob is high up in the ASHTO, and he sent it to all the DOTs. So what the survey that we got is very useful if you want to look at it. Is almost we have 42 states responded. We usually don't get that much. But thanks to them, we get it. So we use that to develop a plan and essentially prioritize what equipment we want to use and what defects we want to do. And I'm going to focus on the results of that plan that we came, and then develop the best use of any devices. Based on the tasks that we discussed, basically, it wasn't very surprising to us. There were 4. First of all, the focus wanted to be on flexible, not rigid. And the 4 defects that wanted to community wants to see in the United States is basically how do you handle the fatigue cracking, rotting, stripping, and delamination debonding. And the 3 equipment that most DOTs voted for was falling in deflectometer, of course, ground penetrating. First, I have to apologize to Dr. Majid. And the third one is the traffic speed. So 1 new technology we are maturing, and 2 really nicely mature technologies that we're doing. So in the dark side, I have what the objective was. So basically what we did is this is the process we went through with all the defects and all the systems. Select the damage mode of interest. You saw the damage modes that we discussed. Articulate deterioration process, when you build it perfectly, time what's going to happen, and see what triggers the initiation of the defects. And find the important parameters and ways to measuring, estimating it, and then establish a threshold where you can see, stuff. So do whatever you're doing, but just be aware of the limitations of the analysis, mostly, and the process. So what we did, we just went and started to simulate all these things that I showed you. We simulated the FWD on top of a pavement as realistic as we could, and the TSD, and then of course GPR. We started doing it. Essentially, we have an asphalt layer, and it can be several layers of asphalt as we're going to discuss, and then you have a base and a subgrade, and then we are looking at the deflection at different points, and we are looking at any possible combination of the modular in the system. So it's a little bit time consuming, right? So each one of the cases, we have around 400,000 to 500,000 simulation of payments that we possibly can see. I should use one example to show you what we did. First thing we did is simulate the response. For this case, I'm showing you an FWD because everybody is aware of it. We simulated, I told you, several 100,000 cases of pavements with different thicknesses and different conditions and so on and so forth. Then we went to the to compute the indices. We found around more than 40 indices in the literature as part of the state of knowledge. So we just used all of them and prioritized them to see what it is. And then calculated percent change from a control. In this case, control would be when it's perfectly okay. In the real world, the control means when it's uniform and you're getting exactly what you want. And then flag the potential defect when it exceeds the threshold, the difference between the defective and the control. And I randomly put it 25% over here. So I want to see at least 25%, and I'm happy that I can see something. Or confident. Now that's we're going to discuss it. So I'm showing you the result, for instance, for a control, delaminated and debugging of that. You see that? Clearly shows me I have to focus on the sensors near the load, nothing new that we know that we don't have. Now we can quantify it. So this is what we're going to get. So I have 43 indices. So we looked at what are the indices that are best, the top 10 of them. Now we can use one of them to show that you have defects. So if it's one good, let's look at two. But you want what? You want two parameters that they are related to best to finding the defect, and you want them not to be correlated to each other. So that becomes just looking in the what's the needle in the haystack, right? So they have to be strongly predictive, but at the same time they have to contradict each other. If you want to put it there, you want to complement each other. You don't want them to confirm each other. So that's what we did. So for instance, in this case for delamination and debonding, you see that we found that the SEI, the old SEI, is a good one. The other one that we found is very good is a base curvature index. If you combination of these two, you can do the best based on the 40 indices that we have. So you see that, when there is in that up one, there is something wrong, if you are in these two zones, there is probably something either delamination or debonding predominantly. And then, if you have a lot of cases that you cannot find if there is defective, we know that because we modeled it, but the FWD is not showing. So that's it. Now, there are two lines over here, 25%, you remember, I arbitrarily just put the 25% just to show you. But now what we are doing right now, we are just trying to balance these things. Okay. What are the balancing your parameters? For instance, I know FWD is more precise than TSD, right? So I want to have that to it. And then there are a lot of science, the terminology and things like that. We're going to discuss it. That's something that we can use to customize it for every different district. How important it is to have some false positive or false negative, Based on that, we can define these very precisely, just to show you. So this is an example of FWD comparing with TSD. And you see that, well, when you get to the thicker asphalt and shallower debonding or delamination, you do a better job than when you have thinner. Because the contrast between the debonded and not is just smaller. And one thing you see, that's what I was telling you, it shows you that TSD does a better job if I use the same criteria of 25%. Probably what I would like to do, I would like to have less than 25% for FWD and significantly more than 25% because the coefficient of variation of TSD, if you're familiar with it, around 20%, 50, 20%, so we want to have more. Anyway, these are the type of work we are doing, and again, like Dr. Mazer, sorry, we are getting into your business, I feel embarrassed. He's the guru. So he started now looking at the same thing, but we are focusing only on debonding and delamination, not getting thicknesses because it's well established and material properties is irrelevant, in this case. And we started now making the debonding and the stripping and looking at the separations from zero is control to so on and so forth. And then just trying to look when we're going to really see it, when we are not going to see it, and develop a chart and guideline. But that's all I have for the first one. I better probably up. I will be 11 minutes or 10 minutes on this one. So I'm going to go to the next one. I don't know if I'm allowed to type it or Laura will get it for it. While you're changing, any questions? Again, I apologize. There's a lot, this is a good discussion, a lot of skip, a lot of processes and thought processes and things like that. I hope you got this. So the next one we're going to start discussing is the TSD. Now, this is a brand new, very exciting, very promising technology. And I'm old enough that I saw, I worked with the first FWD, so just to show my age, So I'm glad that I'm working with the TSD now, and we're going to look at it. So again, the goal over here is to optimize the use of a good technology, right? Okay. Yeah. You can do a lot of things, theoretically, but as my dad used to say, if you shouldn't do some things even if you can, right? So we have to see what just balance the capabilities of the technology with what we expect from it. This one, I have a big group of experts and it's our technical liaison, and boy, it's so wonderful to work with. So we are having a lot of talking about that. This is, it's a great technology and it's improving daily. We have been fortunate enough to work with it. I guess I see Tom, you over here, 2007 in working with Fugro and the project for him to conceptualize it. At that time, no equipment existed. He was very thinking that way ahead of time, and since then we have that doing. So the goal is how we can maximize the information to extract from TSD, given the state of it. Just basically how to minimize the cost of data collection by avoiding where at this moment we cannot get it, and then get some feedback to the manufacturers to see how we can do it. How can we change even the location of the sensors would help, and that's easy to do. So That's the type of work we do. So the goal is to just again do a balance between the TSD capabilities at this moment and analysis approach. So I can equivocally tell you that this TSD in 2016 is significantly worse than 2026. That's incredibly improved. There's room for improvement, but we are getting there. But we have to look at that. So we just get a survey just to see what the potential uses that people want to see and what applications and essentially develop a generic specification for the device. That's what we wanted to do, and that's what we do now and look at it and potential improvements. So again, we did a really nice gap and SWOT analysis. We sent a questionnaire, to all the DOTs, and a lot of you may have received it. What do you want to see from the device, and what do you see as the potential for improvement of the device? So just so that will direct our work over here, and we're just working on the initial framework. I'm just going to go to task 4. That's where we come up with the framework. And this is a tiered approach. There's nothing new in this one. A lot of people are working on this, but this is a little bit on the tiered approach. It's hard to read this one, so I just color-coded it a little bit. So the first step is the QC of the data. We have a lot of great data, but we have a lot of data that doesn't make sense. Do we really want to spend a lot of time on the data that it doesn't make sense, right? Or do you want to average it and just bias your data and so on and so forth? So we look at that. The second one is the processing of the raw data. One of the things is that the devices that we have right now, they measure the velocity. They don't measure deflection. For 40 years, we are conditioned to look at deflection. And the first reaction is to go from velocity to deflection. But seems simple, it's the integration, but it's not as simple when you start integrating and all the problems with the integration. Unfortunately, most people use deflection that the machine provides without looking at the relationship between the two. So the first thing that we are doing, we are just looking at the network level. And network level, there is no reason for sophistication analysis. You want to find where is bad and where is good and so on and so forth before you do project level. We are focusing just on the indices. Let's forget. And what we are doing, we are looking at the deflection indices, but we want to forget that, and we want to use only the indices that we come up because there are no indices for slope. So we have come up with the list of 20 possible indices just feeding from the deflection. So then you use the slope. The raw data that is coming, why do you go to a step that, we have uncertainty and so on and so forth. The next step is the project level analysis based on deflection. And that's something that everybody is comfortable with right now. And the last step is basically the project level analysis based on the slope solely, so that we don't go through that process of conversion. So let's talk a little bit. We have an amazing data scientist. I mean, now having a real data scientist versus us being data scientists is just like going to a Giorgio Armani buying a suit versus going to a second-hand store and see what. These guys know a thing or two that well. ChatGPT and those guys, and in 2022, all of us woke up and became data scientists, right? Thanks to ChatGPT. Anyway, so these are some examples. We just good, fair, and poor, and then what you're doing. several 100,000 simulation. We have to be patient with these things. And then we have a physics-based and we have just judgment-based, methods. And, we have 6, 7 different parameters that we look and just giving a ranking. And depending on your need, we can change and then we rank them. So you know what data is good, what that is, and so on. So that's one. The second thing that we worked on and we are implemented right now is how to get from deflection to how to go from slope to deflection. There's a lot of limitations in that, and we tried hard to make it perfect, but we cannot make it perfect, but we can make it better. Focus on the better data and better methods. There are some assumptions that it's made that may not be realistic, and so we are doing it. So I show you what the methodology. Again, we are data. We are using physically informed neural network. You can see that they know how much we have to reduce the uncertainty. And we are lucky enough to working with TechStat, and every week we are collecting geophone data every week that they're running in Texas. We have proof they're collecting real data and we're comparing with the TSP. So that helps us to improve. And the good thing is that because it's weekly, the pavement has not damage. Usually when we have the time, we have every year or every 2 years. No. We have FWD and we have TSD data every Tuesday that the TSD is in place. So the other one is just basically coming up with the temperature and speed correction. Speed is a factor, is not a big, the temperature is. Again, have that in mind, we have data weekly. So there's no damage. So we use a lot of that to guide us through the process, and we came up with the temperature correction. Again, our goal is to eliminate the using deflection. Just let's start slow. But we have corrections for both slope and the deflection that we have done. So at this moment, so we are done with the tiers. QC procedure. We have applied it to the data, and I guess there's a golden opportunity. We have data from different times at the MnROAD, for instance, and you can see how the quality of the equipment by seeing how many data is now bad or good or clear, and so on and so forth. We have done with the temperature speed adjustment. We are done with improving. There is no perfection. It's just too much analysis to do more 200 miles of the data in one day that we collect to the reverse one. But we improved it. We are working on the back calculation of the layer moduli, and that again, based on this flow, hopefully. And we are just basically introducing some probabilistic approach, because if you look at the data, there's a lot of noise in the data. At this moment, we don't know what's the source of the noise. It cannot all be from the pavement, right? Because FWD should show it. FWD doesn't show the level of noise. But we don't know where it's coming from. If we can instrument the machine and realize separate the source of the noise, then we can do a lot more. But at this moment, we're gonna give you, based on the quality of the data that you have, if you focus only on the good ones, this is the possible range of the information that you can get. And the other step we are doing, we're going stress directly to strength, not to the modulus and then do the calculation. So we said that most probably this is the range. Some of the range you may not like it. Some of them are very nice when the pavement is thinner and more flexible. And the last one is not part of this phase, but it's coming up. Oh, Lauren is mad at me. This is the last one. Okay. You don't want to tell her my integration of Ph.D. data into precision data data. So integrating the deflection, the stresses that you already see or you have seen with the time, and then to come up with the deterioration model. And we are hoping that that will be the next step that we're going to get into, because you might want to combine the functional and the structural information to more important data. Thanks for your patience, bro. I'm done.
All right, good morning. Going to give you an update on what's going on with the rigid team of NRRA. So just a reminder of what we have at MnROAD as far as rigid or concrete sections. Right now we still have 27 mainline active test sections and 24 low line. Mixture of different types of pavement, joint plain, thin fiber reinforced on gravel base. However, those were very thin when they're built and now they're covered with asphalt just to keep the truck running. And then we have an ultra thin fiber reinforced concrete overlay that you all should be able to see on the tour that's been out there almost 14 years now and still active in service. And we still have some original sections, a couple left. It's hard to believe, but they're just sitting out there, obviously proving that if you got 6 inches on a low line road and you build it good, it's got good drainage, it's going to last a very long time. Our main focus has been the lower carbon content concrete pavements. That's really what dominates the test sections on the MnROAD main line. Again, we have 4 different projects going, evaluating the performance of those sections. So again, a lot of construction in 2022 and 2024. Low line, not so much. We haven't constructed anything since 2017, so almost 10 years. And then we heard a little bit about yesterday from Julio on the construction of that DCSA section that's out there. And this just gives kind of a timeline here of where we're at with a lot of these research projects. Again, the first 3 there are related to the 2022 sections. You can see we're almost done with those. And we saw that we have some funding. We're going to be extending the monitoring of those 2022 sections for several more years. And so those projects will probably start later this fall. And once we get access, get out there and start more detailed monitoring again. Then we have this, the next presentation will be an update on the automated 3D GPR analysis. And that's what project we teamed up with the Intelligent Construction team on. We had the 2024 construction support project, which was Larry Sider involved in kind of developing the sections that we put out in 2024. He's kind of wrapping up some testing results with that particular project. We have the next one is, again, the monitoring the performance of the 2024 sections, a few less of those, but nevertheless, another suite of tests. So you can see we've only got a couple of years on those, so that project has quite a ways to go. We also have this project on use of microspheres to kind of replace air training agents. That project is pretty well along, although I think there's going to be, again, another year of monitoring that, so that won't wrap up until the end of 27. And then we have, again, the CTS rapid set section that just started, and that also includes another section or involves some study of smaller diameter dowel bars within it. And then a couple of projects, I'm actually PI with my colleague Mike Wallace. This is kind of a combination of both Minnesota statewide research and MnROAD test sections associated with NRRA. And that's, again, this concept of using early loading to increase joint deployment in your thin concrete overlays on asphalt. We're going to be wrapping that up in the next couple of months. Then we had another project, again, including test sections, but also some projects in Minnesota on concrete overlay test section repairs, predominantly looking at, diamond grinding, something that has faulting, and how long does that faulting, how many more years till it redevelops into the same faulting you started with. So That one is, we're getting requests to extend the county, monitoring the county project, and also we want to get more data on the I-35. And then another one that's should be of interest to the group is the study of the concrete roundabout performance. We saw a poster out there with some preliminary results from that. So again, just going around our entire state, looking for various designs and seeing how they're performing since they've been built. And then I mentioned before, there's also this independent project we've been working on evaluating smaller diameter dowel bars. And there's a good chance that when we redesign or design some sections on the low volume road next year, we'll probably include other variables and other various diameters and really look at optimizing dowel bar diameters. So if you're ever interested again to see where we're at and also results, all our task reports are posted. Again, you can go to our website. And with that, I'm going to introduce Ken Mazer, and he's going to give us an update on this 3D GPR project that we have going.
Thanks, Laura. Thank you, Tom. So I'm going to be presenting on this 3D GPR analysis of concrete pavement. For concrete pavement, this is a project. This is an NRRA project. Shungtao Dai has been our technical liaison and extremely helpful throughout this. It's a joint project between my company InfoSense and Marquette University. My co-PI is Majid Hayat. So the initial objective of the project was to identify missing, misplaced, and misaligned dowel and tie bars, and also other defects in concrete pavement, including voids, under joints, and but the focus of the project has really been strictly on dowels and tie bars. So the issues that we're addressing are various types of misalignment. This is a figure from the literature: horizontal translation, longitudinal translation, skew in the horizontal and vertical plane, and vertical translation. So these are looking for various types of misplacements, plus simply the absence of the dowel and tie bars. Consequence, if dowels are, for example, in dowels, if they're misaligned, they can cause joint locking and eventual damage to the concrete pavement. So the idea is to be able to detect these sort of conditions as early as possible so that these types of damage can be mitigated. The technique employed in this project is to use 3D GPR. So that's distinct from conventional GPR, which generally uses an antenna or two antennas that go down the road and give you a single line of data that gives you how things vary longitudinally, but you don't get much information across the width of the road. This 3D GPR system has a series of sensor elements across the width of the unit. So each of these red things on the top there, transmitters, and on the bottom is receivers, 10 on the top, 10 on the bottom, and each transmits into a pair of the others. So you wind up with 20 channels spaced at 3 inches apart. It gives you quite a bit of detail across the width of the road, which is the kind of detail you need to identify dowels and tie bars. They come in two different varieties. The ground couple is a unit that slides across the top of the pavement, and the air launch is elevated, and each has advantages and disadvantages, and I'll explain that in a second. So on the left is a ground coupled system. Because it's sliding on the ground, you can only go about 20 miles an hour, but you get a lot more detail because you're much closer to what you're looking at. Whereas the air launch system enables you to go 50 miles an hour, but you compromise the level of detail. So each has its pluses and minuses. But the dowels and tie bars show up very clearly in this data. This is an image from a program that reads the 3D GPR data. And the top image is a slice vertically through the road. The bottom image is a slice horizontally at depth of the steel. And the right-hand image is a slice across the road. So in the top, all these little blips are individual tie bars. and they actually have a little hyperbolic shape to them. And then when you take the slice horizontally at the blue line, you see all those tie bars laid out on the bottom, spaced at about 3 feet apart. And then every 15 feet, there are dowels. So that's, data shows up very clear. This is similar, that previous data was a ground coupled system. This data is from an air launch system. You see the same features, you can see the dowels and the tie bars, but they're just a little blurry, not quite as crisp, but the information is there. And you look at the bottom here, you can very easily see where something is missing. There's no tie bar in this little gap here. So we can see it. We can see the issues looking at the data, but when you're looking at a couple of miles, you don't want to have to do this visually for miles of data. So the goal here is to really be able to automate the detection of these issues, and then the user can always confirm and go look and say, is it really missing there, or is it really spread? So that's really what we're aiming for. Also, things like this data is very compressed now. This is 300 feet worth of data, and the little blips are the tie bars, and the bigger blips are the dowels. And you can see there's quite a depth variation, which is not normally expected. So this kind of information can get readily output with the kind of software that we're developing. So the algorithm that we have developed basically first tries to figure out where, in this big mass of data, where are the dowels and tie bars? And then it goes to those locations and fits these hyperbolas into those locations to get where get points on the bars. And then those points are connected with a line to make a bar. And then we calculate the properties of those bars, the slope, the position, slope vertically, slope horizontally, etc. So and I'll just show you those steps here. So this is called a mass. It's kind of an image processing thing where the red blotches are where the dowels are on the left, and then additional red blotches on the right are where the tie bars. And the reason we have to do this is because, it just as an example, in a mile of data, there's 100,000 scans. That's how much data we're collecting. Each scan has 20 channels. So that's 2 million sort of channels of data. And each channel has 256 points. So that's 512 million data points. So we really we have to know where should we look in this mass of data to find the dowels and tie bars. So that's really the goal of this step. And then once we know where things are, then we fit these hyperbolas to them. So when an antenna goes over a bar, it produces this hyperbolic shape. That shape is really the hypotenuse of this little right triangle. It's just from geometry. So when we go to these locations, we see the points, we fit this hyperbola, and we say the peak of the hyperbola is the location of the bar, both in the horizontal plane and vertically. So then we get a bunch of these points, and then we use something called cluster analysis. It groups a set of points that are in the same neighborhood. And the cluster analysis produces something like this. Each of these different colors are a different cluster. On the left are the dowel clusters, on the right are the tie bar clusters. So once we have these clusters, they're a bunch of points. All we have to do is fit a line through the points, and that line gives us our bar. And then all the properties of that line are the things that we're interested in outputting. So our initial results look something like this, where each bar has an ID. These are tie bars. It has a number of points that were found that made up the bar. It has a distance. The center of that bar is a certain distance from the start. It has a certain depth. It has a certain angle. These are referenced to 90 degrees, and they have a certain spacing, which looks like it's about 3 feet, which is what it should be. So this is just a spreadsheet. We can take this spreadsheet and filter out locations where the bars are, let's say, greater than 10 feet apart, because that would be something wrong. So we do that. We got a bunch of locations in this spreadsheet. And this is my comment that there was actually something missing. So just as an example, the first one here is at a distance of 1,200 feet from the start. And this is what we found. Here's a big gap. So very quickly, we can zero in on these locations. This data, by the way, is from Highway 23 in Wisconsin, Fond du Lac, right near Fond du Lac. And it happens to be a road where we knew from previous work had missing tie bars. So it wasn't just at random. But it was a good data set to do testing and development on. Okay. So we felt, okay, we were finding what we need to know, but how good are we doing? So we went through a process where we established ground truth to see how accurately are we detecting bars. We established ground truth where there was a data set that had all the points, all the bars kind of laid out. And then we went through the automated process and we compared how our detections match with where the bars were supposed to be located. And we wound up getting kind of an accuracy on the order of 88 to 95%, meaning out of all of the dowel bars, for example, we got the locations between 88 and 95% correct. That's pretty good. It's not the greatest, but that was initial, and we've made some improvements since then, but we felt we were on the right track. And this is just an example of how we did that. So these blue circles, the blue circles are our ground truth. We had somebody just go in there and, put their cursor on every bar they saw. And then the yellow ones are what the program came up with. And basically the accuracy was, how close. If we use a criteria, like if we're within a foot of the ground truth, then we found. And that's where we got those accuracies. You can see pretty much we did pretty well, except we missed a couple over here. But that's the process that went on. So the goal is really to give the DOT folks a tool to do this analysis. So we came up with a graphical user interface, or GUI, as they call it. And basically the user can just select a folder, read in a file that has all the 3D GPR data. There's also a file that has the coordinates lat long. Read that in, just say load the data. Data gets loaded. You can see there's about 2,400 feet worth of data here. It just shows you kind of the statistics of the data that you just loaded. And then you press a button and you say run analysis, and it runs. It's pretty simple. There are a couple of parameters and things, or you can say, for example, I don't want to do the whole 2,400 feet. I want to zero in on between 500 and 1,000. So you can do that. You can say, okay, is this data ground coupled or is it air coupled? You can choose that, and you can choose, do you want to do a joints and dowel analysis or a tie bar? So the two separate kind of analysis. So that's pretty much it. And the other, so you just say run, it runs, and then you can do something which is similar to what I just mentioned, is do a query. You can say, for example, find me all of the dowel bars that are spaced more than 2 feet away from the neighboring dowel bar. That's a query, and it will spit out results just for that query. So, so the things that the program is outputting, similar to what I showed before, is horizontal spacing, longitudinal translation, angle in the horizontal and vertical plane, and vertical translation. And there are 4 kinds of outputs. There's statistical output, where we see how these things are distributed. So if we look in the middle at depth, for example, we can see that on the average, these dowels are 5 inches down, but this is how the depth is distributed. And we can look, for example, at the horizontal spacing, which is supposed to be 1 foot, and it typically is, but there are some outliers. So you can get like the big picture with the statistical output. You also get tabular output, which every single dowel is shown and where it's located and what it's lat long and what its depth, spacing from the neighborhood dowel, longitudinal translation from the average joint location and the angles. And then we can get GPS, or what's it called, Google Earth. It'll plot out all the dowels, the yellow points, And then we can import it into that program that shows where those points are relative to the GPR data, so you can see how things came out. So that's kind of handy. I mentioned the query. So this particular query was find me bars that are more than 2 feet from the neighboring bar. And you can see the red dots are the result of that query. So it finds those things pretty well. You can also just, whoops, there's something else here. No, okay. So that's where we are. Where the status is that the software has been tested on a select number of road segments. A preliminary version has been supplied to the TAP members of the team, and they're trying out. We've got some feedback. Based on the feedback, we've made some improvements in the accuracy. We also made some improvements in the processing speed, and we are coming up with another version that we're going to be delivering in the next couple of weeks. And project should be wrapping up by the end of July. Final report. So that's it. Thank you.
We'll take time. Anyone have one question? Ken? Oh, there we go. Take one question. Keep us on track for time.
Very good presentation. What is the accuracy of the GPR in terms of estimating the depth of the downloads?
The accuracy or the precision? Well, okay, I mean, accuracy is how close you are to the actual, to the real depth. Precision is to what degree of, within half an inch or whatever. Precise. The accuracy really depends on what you use for the velocity. And for this particular project, we've had to estimate the velocity. So what you're going to get are the relative depths of the bar, not necessarily precise, absolute. There are ways to tie down that velocity, but at this point, we're looking more at relative, rather than absolute.
Okay, for the flex team portion here today. And so Michael and Ishan will be presenting us some really interesting topics. I think you will enjoy them in a few moments. So I'm just going to take a few minutes and just kind of go over some of the accomplishments and successes we enjoyed here as a flex team this year. So one of the things that comes to mind is the extra money that was approved by the executive committee, $500,000, and that was distributed evenly amongst the teams. So once we heard that was going, we as team submitted or solicited for topics from the members, and once we got it back, then we sent them out for ranking, and the one that had the most interest was the spray rejuvenator test section. Continued evaluation of that, and PI on that is Cal Morris from NCAP, so congratulations to Cal. Also, the recycled binder availability contract signed. Chris Williams, the PI from the University of Iowa, so congratulations, Chris, as well. And I also have a research pays off. I think that's for all the teams. I think it was a success all year. Really good presentations. Flex team had actually 4 presentations. Really good ones from Josias and Ishan Dave and Fan Yin, as well as Dave Johnson. And another one that kind of is really benefits us all as a team is getting the data collected in MnROAD. It was quite an effort this year because all the had to do it mostly on live traffic, so they did a great job of getting all that for us. Continuing on here, so these are just a few ideas that we have maybe for consideration for phase 3 as we move into it. And by no means a completed list. We've still got time to get some in. So start thinking about it, like Michael was saying this morning. And hopefully we can get some good ones and I guess we really haven't got a lot of time, maybe the end of June, so we really want to get going and start looking at some of these, so. So, you know, it's gonna be exciting going into phase 3. And, you know, hopefully we'll get some of these ideas going where we get some test sections and maybe some lab studies or synthesis or something. Maybe all 3, so. And also, as Mike went through this morning, it'd be, you know, what can we do as a flex team to, you know, that benefits the other teams. I think it's good to work with the other teams, share research initiatives and things like that. Also, maybe focus on how do we implement these things too, so we got it done, so while I'm, you know, excited about phase 3, I'm also excited about the research we got going right now, and, you know, I think we got a lot of things going that, you know, are going to answer a lot of questions and needs for other agencies, like, you know, how much RAP can we use? And, you know, how can we make our pavements more, you know, perpetual? How can we control cracking, whether it's load related or reflective or thermal? So, you know, I think our research is really on the point there, so I guess it's just, mostly I'm up here today to thank everyone, all the Flex team members for all they've accomplished here and all the successes we have. And I also want to thank Kurt and Mark and Ben for leading us, and for Lauren for all the things that she coordinates and research things off and things like that. Also, I want to thank Mike for helping me with all my charities. I don't think there's a week goes by and to talk to Michael. So with that, I'm gonna just let Michael go ahead and speak on the present on the MnROAD test sections that Flexible Team has.
Yes, and before I get into that, I really want to acknowledge Kurt and all the time that he puts into this. I've really enjoyed the relationship that we've built over the years and looking forward to keeping it going. Eventually passing the torch on, so you don't feel like you're on a life sentence, but we enjoy working with you, and thanks for all you do and your leadership, really trying to make the Flex team meetings more dynamic and generating more discussion and conversation. So thanks, Kurt.
Thank you, thank you.
And one more thank you to Lauren for keeping us on schedule and handling all the IT stuff, all the presenters who realized 3 minutes before that they had their own presentation email this morning and got us a late start. So thank you, Lauren. Really appreciate everything you do. So I will be giving a field performance update of our MnROAD test sections, and then Dr. Ishan Dave will be talking about the actual research analysis and his ongoing efforts with this. So this is a very large project. It's also related to the project that Bill spoke on yesterday. We truly could present on just this project with the study. There's companion sections at Auburn's test track in Alabama. There's a companion section that Bill talked about. We could talk about this study for a full week. We could do a week seminar on all this data set. So my challenge is to do it in 10 minutes, and I've already wasted 3 of those minutes. So, MnROAD performance update, I don't have it on here. The perpetual pavement sections that we built in 2022 are behaving perpetually, so there's no distress or performance update to put on there. So those are in good shape. The MnROAD reflective cracking challenge is what we actually saw some good action happening over our cold temperatures this winter, and that's what I'll be covering today. So my wordiest slide that I have, but the winter that we had this year was the most severe, or we got the lowest temperatures that we've had in the last 5 years. At the beginning of January 2026, we had 5 test sections that were not cracked. By the end of the month, we had only 2 test sections left that were cracked. All cracking that I'm talking about today throughout the entire presentation and that we've seen in the MnROAD portion of this study is reflective cracks over saw cuts that we artificially put in the lower lifts that we do where to monitor crack progression. There's 7 saw cuts in each cell. So that equals a total possible crack potential of 168 feet of reflective cracking. A little bit different than some of the previous MnROAD data sets. These were all captured and measured from the shoulder visually under live traffic. We aren't able to close traffic right now due to some reconstruction, lane additions going through the area. So we'll get our kind of ground truth numbers, but Jacob and I looked at this a lot, you guys will see. So we're fairly confident in the numbers we're reporting. Test section setup. So we have 10 of these set up in the first mile of MnROAD's main line or interstate test section. So we took our typical 400-foot test section and literally saw cut it in half in the lower layers. So our bottom 4 inches of asphalt has a cut through it in half the sections. These are meant to replicate naturally occurring transverse cracks, really trying to give an even platform to evaluate overlay performance in these unique surface mixtures. We have 10 mixtures here. I'll show the full results at the very end, but I'm going to kind of use these 4 to highlight kind of the spread in data that we see throughout. Also want to point out that we have 200 feet that is uncut, new construction, where we can let naturally occurring, especially low temperature cracking, occur. So our first crack that we saw, we did not have any cracking through the first 2 winters. And then prior to Martin Luther King weekend in 2025, we had a cold stretch coming. I called Jacob Calvert on a Friday. He was able to go out and check the sections. We had no cracking. We had a holiday weekend. Jacob was back out there on Tuesday. We had cracking. We went and documented it. So we were able to isolate it to a single weather event where we got our cracking. And then this year, as winter came, we did a similar thing, and we had kind of closer monitoring as we had some cold temperatures. And we got a single low event in December that was minus 27 Celsius. And then our cold snap again this year with Martin Luther King weekend, all the way down to minus 30. And then additionally, we got some more information on whether it's low temperature, extreme low temperature magnitude, or if it is more kind of the duration held at longer temperatures. So very detailed information that we can kind of dig in and provide Bill detailed values for the monitoring or the modeling things that he showed yesterday in his presentation. So surrounding these dates and temperature swings, Jacob Calvert and I did a lot of distress surveys in January. So just focusing on January and the 4 sections I'm highlighting. So the PG 58H minus 34, which is one of our common modified MnDOT binders going into January, had 2 out of the 7 sections cracked and really didn't change a whole lot. You can contrast that with the Aramid fiber section had no, or one of the fiber sections, no cracking going in. And then 4 of the 7 cracks appeared over that month. But still, the total magnitude is very, very low. And then on the opposite end, our 5828, a minus 28 binder grade, so not as good low temperature cracking performance. And we had 7 out of 7 reflective cracks going in. Most of those occurred, 5 out of 7 of those occurred on January 2025 Martin Luther King. And then just a little bit kind of finishing out the lane cracking in that section. Yeah. Exactly. Yep. And I'll zoom in on some of these pictures, and as part of the visual takeaway here. So we are taking the same picture over time to monitor crack reflection. We have a mark here that we located with our GPS that tells us where the saw cut is underneath. And then we're finding that when we do our distress surveys and saying, nope, no cracks in this one. This one was 5 feet, this one was 6, et cetera, et cetera. So you can see this is one of the big contrasts I want to point out. So these are the cracks in the 58H minus 34, fairly tight. You have to use the edge stripe to kind of go locate it and then follow it up. No cracks in the 49 minus 34, and then obvious real wide cracks in our 58S minus 28, and then starting to deteriorate along those cracks as well. And then the Aramid fiber, so this was a no cracking, and then on the 29th, there is cracking. Just to show you what we're talking about, when we say there is cracking, you follow it up through the edge stripe and there is a crack there. But that's how difficult it is to see or how tight those cracks are. All right, so wrapping it all up, kind of our total cracking performance, and this is really where the value of this experiment is really coming together. We have test sections now that still have 0% cracking, and then we have test sections that are almost 100% reflected through, and then we have all of our different additives and other sections somewhere in between. So we got a nice spread of data to work with and really dig into the data set we have, and then share that and let everybody dig into it as well. We won't be able to visit these sections on the tour today, so this is MnROAD this morning. These our test sections that I talked about are up here, kind of by that pond. This is westbound traffic. This would be westbound traffic. These cameras are going different directions. So westbound, this is MnROAD over here. This is where we'll be visiting Raul and Jaron for the corner reflector study. This is the new alignment that was constructed last summer. It is going to be the new westbound alignment. Right now it has eastbound traffic. So in the future, we'll be able to divert MnROAD traffic from here, test sections, to here with the normal 3-lane westbound lane. All right, now turning it over to Ishan.
All right, I'm going to try my best for us to be done in 12 minutes here. Mic is turned off. How about now? Awesome. All right. Michael already set you up, so I don't need to go through a lot of initial part. One thing I will mention that on your way to MnROAD this afternoon, if you miss your exit to get off, get to MnROAD, you'll get to drive on the exit. So there's your incentive to miss the exit. Lot of people to thank, obviously, Mason Khorshidi and Sadek Tormos, graduate students working on this, doing most of the work. And as you saw from Michael's presentation, all the time and effort that him and Jacob have put into these sections and collecting data for us. It's not, I'm just talking about it, but it's not just me, the research team, it's myself, NCAT, and also Heritage Group. They're all part of this team together with folks from MIT with the presentation that you saw that Dr. Butler made yesterday. All right, that's going to work this way. So I won't go through the objectives and things like that. I think pretty much everyone in room at this point knows why these sections were constructed, what we are trying to accomplish. You already know where they are. Michael's already shown you what the layout looks like. He's already told you about different materials that are used. As mentioned, this is a companion study to the additive group experiment. That's, again, a joint effort between NCAT and MnROAD, a pooled fund. And here we have some sections that are in addition to what are part of additive group. So you do have a section that's the 58V minus 34 control, and then also the underlying mix that we have with the 58S minus 28 that doesn't have any of the additives in there. So very quickly, and we did a research base off last year. I presented these results also at this venue last year, so I won't show you all the lab results, just the updated results. Task 2 is fully completed. We did kitchen sink approach, pretty much every cracking test that we could get our hands on that are used by any of the NRRA agencies were run as part of this experiment. And the only results I'll show you today are the newer ones, which are Illinois Flexibility Index test results that Illinois DOT conducted last year, summer and fall, and also some uniaxial thermal stress strain tests that we conducted later last year. And then I'll give you a quick update on models. Again, this were presented as part of one of the research phase offs. If you have more interest in learning more about these, please go back and watch that. iFit, I think most people in room would know what iFit testing is. So it's a semicircular specimen with a notch. You're running the test, trying to get a feel for what's the energy that it takes to break this material, but also give some credit to the speed at which the crack would propagate by looking at this post-peak slope. And there are different variants of it. Ideal CT, if you run that, CT index also considers this. We have work going on with MnDOT that's looking at other indices that also look at the post-peak shape related parameters to really get to the cracking performance of mixes. Illinois DOT ran these tests. Minimum testing requirement for Mercy is that we do everything on reheated mix and the critical aging procedure, which is essentially 6 hours at 135 degrees Celsius mix aging, which is one of the procedures in AASHTO T393. Illinois DOT also has one of the procedures in AASHTO T393, where it's a compacted SCB specimen that is aged at 95 degrees Celsius, and then that's tested. So since that's their default, they also did the alternative long-term aging, and you can see the effects here. You can see all the different materials that Michael showed to you. As we can see, most of these mixes do meet Illinois DOT's threshold, which is 7.5, and that's on reheated mixture, except for that control, which is also the mix that had already cracked in 2025. So as you can already start to see that lab testing is aligning with what we saw at MnROAD. So bottom line, that 58S minus 28 and also the 58 minus 34 or 58V minus 34 control, those two had the lowest FI, which are also the ones that actually showed the most inferior reflective cracking performance so far. Some mixes, especially wet rubber, very resilient to aging. We didn't really see much transition in its properties after aging. Uniaxial thermal stress strain test, if you're not familiar with it, it's test developed by University of Nevada, Reno. It's really a fundamental property of mix and more so important in places like MnROAD, where you're going to see these very cold snaps. It's really looking at how your mixture contracts as temperatures drop and what kind of stresses are generated for that material to crack. We did set this up last year, and we did conduct tests on all the Mercy mixes. Because it uses so much material, we had to focus on just doing testing with long-term age material, because you are having to construct two sets of samples for every single test. One is restrained and one is free. You get stress data from the restrained one, strain data from the free one, and then do multiple replicates. Just showing snapshot of one set of results, and what we are looking here, if we just pay attention to these bars, think of it as a mixture level thresholds to your PG grading system, right? On a PG grading system, we have low temperature grade, which is temperature at which you have things like M value go below 0.300, stiffness go over 300 megapascals. Here, what we are looking at is temperatures at which behavior of material goes from having this stress relaxation capability to more glassy response, and temperatures at which those restrained specimens would actually crack. Okay, so if you think about the old DSRST, you just get this red bar. Here we also get this transition of materials from viscoelastic to glassy state. And once again, you can see that even if you have just minus 34 grades, doesn't mean that all of those mixtures give you that same temperature at which cracking can happen. These lines are set up with the PG grade line, so you're minus 34, 28, and so on. Once again, no surprise there, minus 28 didn't show as good of a mixture cracking. Again, you don't expect this minus 28 to match with this, because that's on binder, this is on mixture, different rates, things like that. But overall trends agree with what we had seen, and you can also see how the fibers have done quite well here, and also some of the rubber mixtures, the dry one did quite well. So key observations, what we learned from all the lab testing that we did, and again, this task report is on NRRA website, so please look through it if you have questions or contact me. But in general, additive treated mixtures outperformed anything that was not treated with additives. Amongst the controls, the 58H minus 34 performed quite well, comparable to a lot of additive treated mixtures. 58V minus 34, not so much. And that's a little bit of head scratcher, because you go from H to V. And then within treated mixtures, the rubber and fiber modified mixtures in general showed better performance than those treated with plastic. Modeling side, so once again, somewhat of a kitchen sink approach. We tried to get our hands on all type of commercially or freely available models that we could apply just to show the breadth of modeling that can be used when you're looking at reflective or thermal cracking. Obviously, we wanted to include AAA Pavement ME, FlexPave, which is the Federal Highways product, and doesn't do reflective, but looks into thermal side of things. Texacoal, which is developed at TTI and uses Texas Overlay Tester as primary input, and LETC, which was developed through a full fund study on low temperature cracking. Again, these two primarily focusing on just the thermal side. And there are inputs and things like that that go with them. I won't go through that. Like you saw in Michael's presentation, and Bill mentioned this too yesterday, with overlays, you oftentimes see this S shape, right? Where you are starting to form some cracks, and then all of a sudden next year, with continued traffic, you have this steep increase in cracking until you get to 100% cracking state. And that's what most models showed us. So that makes sense, nothing surprising there. But we wanted to also see how to convert this into a single number or index to make comparisons. We did what we had developed in the previous NRRA effort. All this index does is it looks at area under that S-shaped curve and normalizes for time. The reason to do that is so that you can essentially give credit to mixtures that crack later than earlier. Okay, so that's the only advantage here by using this type of index. So if we look at results in terms of this index, higher number is bad. That means that your mix is cracking at a faster rate and is cracking earlier. You can again see how different software predict it. Again, this is not reality. This is what models tell us. And if you look at Pavement ME, it actually predicts that the control mixture to crack to a better perform, to not have as good of a performance as some of the other additive mixtures. So that aligns with field, but also one of the mixture that's doing really well in the field, as you saw in Michael's presentation, it doesn't really give that one a credit. So obviously models are not perfect, and you can see that there. With Texacoal, again, if you compare to what Michael showed, this one does a little bit better, especially for the additive group mixtures. Once again, that 4934 Rockstar mixture in field, the model doesn't really see that benefit. So we do have some comparisons, and again, I wouldn't go through all of them, but just wanted to highlight that if you look at these different type of models, you can really end up with any scenario that you want is the take, right? So we need to make sure that we are doing good job comparing to field, and that's the whole reason why we construct pavement test sections and not just rely on models. And you can also see that some of these do better than others in terms of being able to predict that 58S minus 28 is not going to do well, and you 4934 can actually do better, as you see in this case of LETC. But keep in mind, this just looking at thermal cracking, it's not looking at reflective cracking within the context of model itself. So where we are now, we have done these models, existing packaged models, and now we are doing what Bill